Good morning, sir. Puneet, sir, good morning. I request you to please check. I have assigned the privilege to you as a presenter. Yeah. Hello, Puneet, sir. Is my audio clear?
Yeah, are you able to hear me?
Yeah, I'm able to hear you. So,
All right.
already a reminder has been given to all the participants. They are joining. So, should we wait for 2 minutes or we can start, sir?
Yeah, we can wait for 2 minutes.
Okay, yeah. Thank you.
Okay, can we start?
Yes, sir, we can start, sir.
All right.
So good morning, Puneet sir and all the participants. We are starting with the day 6 session. So I request you all to please note that today we are having an MCQ. So be connected with us. Thank you, Puneet sir. You may start, sir.
Okay, I'll quickly cover what we covered on day 5. That will be a recap. And then we will cover TLMs today, transaction level modeling along with TLM ports. And we will also look at our test benches and look at them from the connectivity perspective, how different TLM ports are connected and how transaction flows from one place to another. Okay, from one component to another component. So that's what the agenda will be for today. We'll also be covering in the lab sessions. We'll be making new test cases, and we will be modifying the earlier test cases. We'll try to override constraints to create new test cases. And then tomorrow you will be having a session with Ritesh, and we will be talking about um, how to map an RTL to uh, using Quartus, how to map it to FPGA and how to access it from software. Day after tomorrow, I have a session on QEMU where we'll see how to interface the QEMU emulation platform. And that's a software emulation platform with the test bench, with the UVM, embedded UVM test bench. So there'll be some interesting stuff there. And then on Thursday, we'll be covering how to run a test bench, embedded UVM test bench on an embedded platform that will be D10 Nano and perhaps D10 Standard as well, depending on how much time we have. And then Friday will be an interesting day with Intel, where we'll talk about uh, advanced technology that works with SoC FPGAs, so advanced toolset and advanced technology, how to use SoC FPGAs. Okay, so let's start with today's stuff. So what I am supposed to do is I'll have a recap of what we covered day before yesterday. Just let me bring up the slides. All right. Uh, so, okay, not this one here. So I need to pick up the slides for day 4 and day 5. Okay, not this format. Just give me a second. So day 3 slides. Probably these ones. Okay, so I'll want to cover the object-oriented part very quickly so that we can relate it to some of the concepts we'll be learning today. So the four perils of non-agile design: immobility, rigidity, and then you have fragility and viscosity. These are the four bad smells of software which we want to avoid. Otherwise, we can't make reusable software and we can't scale software. We'll have too many bindings, and therefore things will be very difficult to reuse. And then we talked about how a test bench is layered. A layered test bench will have UVM base class library right at the top. And that's how base class library usually works, where the top level algorithm is created and the details are filled using dependency inversion principle. Okay, so we'll go through the dependency inversion principle once more along with interface segregation principle. Okay, so now this also is important. Every class is a contract, and we will be covering TLM ports today, and every TLM port is an interface actually, and every interface is a contract. So by way of connecting various components via TLM ports and exports, we are actually allowing reusability, because we are like when a layer connects to, say, a sequencer layer connects to another sequencer layer, it's through TLM ports. And if we bring in another sequencer which could be doing something else for another test case, for example, then we can just plug it in, and we can take this sequencer, maybe which is creating SHA3 sequences, to another test bench which may not be using Avalon bus but could be using Avalon AXI bus, and we'll be able to connect the same sequencer and same driver there through TLM ports. And that's how connectivity will be managed through interfaces, and interfaces are basically TLM ports are the constructs in UVM which implement interfaces. Okay, so single responsibility principle, open close principle. I hope you all remember it. And then we have that example of modems, and that's how we had illustrated using this example how the upper layer doesn't depend on the lower layer. And then we went through this cost substitution principle. We had that square example, how square is not a rectangle. And then we had ISA versus HASA, and we saw how, one important thing here is a relationship basically means inheritance, and has a relationship means um, basically aggregation or composition. So a computer has a monitor, a computer has a processor. Similarly, you have is a relationship where you have, for example, a keyboard is a USB device and a mouse is a USB device. Okay, so that way. Now the thing over here is which I want to emphasize. It's most of the times in 80% cases you will require has a relationship, and only in 20% cases you require is a relationship. And but uh, a lot of people tend to overuse is a or overuse inheritance, because it's a difficult concept to learn, and once they have learned it, they want to apply it everywhere. So on the other hand, it's applicable only in, a ballpark figure is 20% cases, and that's where you should apply it. So it's one concept which is overused by coders. Okay, we went through dependency inversion principle. So what we do is we create interfaces, and these interfaces are nothing but base class components of the service we need from the lower layer. Okay, and in the lower layer, we will provide the service by implementing this base class. So we'll inherit from this base class and we will put in the details. So the same thing we will see later on how the same thing um, is explained via design patterns. Then we had interface segregation principle. It's yet another principle which is important for understanding how TLM ports work, TLM ports and exports work, because we have a TLM port or export this mechanism for each of the component will be interfacing with will have a separate TLM port and export. So another thing which has basis on interface segregation principle. Okay, so then we quickly go over the design patterns. We have template method pattern. One of the examples I had given was the income tax procedure where we get a software and we fill in our details into the software. It may be an Excel sheet, but it's a software and we put in our details. So it's like a template that we fill in, and then the top level algorithm how to calculate the income tax based on our details is applied, and we get to know what our income tax would be for the current year. Similarly, for strategy pattern, we saw how strategy pattern is similar to template method pattern, and both of them have their roots in dependency inversion principle. But strategy pattern also has its root into the interface segregation principle. So we have, you know, for multiple uh, objects, for example, if we talk about GST, then in GST we would have, like if you compare it with income tax, GST tax would be based on the different services we have provided or different services may have taken from vendors, and similarly what we have purchased or sold to various clients or vendors. So now with strategy pattern, what would happen is that each of the component or each of the product in the GST example, each of the product that we have sold, each product will have its contribution towards calculation of GST. So in any GST software, the project, the object that we have sold, the product we have sold, it will be there'll be an algorithm. So we delegate to that algorithm and we find out the GST component due to that product, and that is used in the top level algorithm to calculate the overall GST, whatever GST I have to pay to the state government or to the central government. That way. Okay, then we talked about facade pattern, which is nothing but wherein we say that we need the same interface for, so it's not like the same interface object log. It's important to understand to distinguish between interface segregation principle and facade pattern. Facade pattern says it has to be the same interface for the same client, and you can't deal with a client with different interfaces every time a client requests service from you. Interface segregation principle, so facade is about something common, like every time a client wants to access a particular service, we provide the same interface, while interface segregation principle says for different clients have different interfaces. All right, so that's the difference over here, though they seem slightly contradictory in nature. Singleton pattern, and we saw how some of the UVM components, like the UVM root and the UVM printer, you have different utilities, and there are UVM. So for implementing those utilities, UVM base class library has various components, including UVM packer, UVM copier, and so on. So those are all singleton. Okay, and even the UVM phases, like you have run phase, it's a singleton. The same phase, if we are going through run phase or, for example, through build phase, the same phase passes, the handle to the same phase gets passed to all the components, and thereby on that phase. So, for example, if it's run phase, then on run phase we can raise or drop objections because it's the same component or the same object which is getting passed to the various components which constitute our test bench. And because of singleton pattern, because all the phases are singleton in nature, so thereby we are able to use the objection mechanism. If there were different objects, then objection would be raised for different phases, because phases are now different objects. They are, for every component there is a, though it is run phase, but the object is different from what other components are having. So that will be utter chaos. That's why every phase is singleton. So the same handle is passed on to all the UVM components. All right. Then we have factory pattern, and we saw how factory pattern basically is an implementation of dependency inversion. So template and strategy pattern uh, are also implementation of interface inversion, but they need virtual functions. And for, as we know, for every class has a constructor, and constructor cannot be virtual. Destructor can be virtual. Constructor is the only method which is not allowed to be virtual. Okay, why? Because if it is virtual, if constructor itself is virtual, then we will be able to instantiate. For example, we'll be able to instantiate an abstract class, which cannot happen, right, from the concepts itself. So at the time of constructing an object, we need a concrete class. We can't have an abstract class. For example, we just can't say construct a shape. We need to say what kind of shape it is. For example, we need to say it's a square that I'm constructing or a rectangle I'm constructing. Though all instances of rectangles or squares or circles, by way of inheritance, all of them are a shape. So once they are constructed, I can treat them as shape. I can say, give me area of this shape, and I don't need to worry about what kind of shape it is. It will be taken care by way of polymorphism, and the area will be given to me. So then we had observer pattern, which is basically an implementation of open close principle. So it derives from open close principle, and an implementation of observer pattern in embedded in UVM or embedded UVM as well is the callback mechanism. All right. So we go ahead, and then the different examples I gave for each of these patterns. Okay. So then that was what we discussed on day 4 and day 5. So today we are going to go through TLM. So first we'll learn the concepts of what transaction level modeling is about. We already saw some examples of TLM modeling and had briefly talked about TLM when I said when you have a transaction as a software object and it plays on the BFM. So BFM is the bus functional model in Verilog, is the one which converts a transaction from a software object to its signal level view. So that was our understanding of TLM. But in many cases, a transaction may just have a software view because uh, that would be actually in the TLM world. That would be more often that it only has a software view. It doesn't have a signal view, because signals, once you once you take a signal view of a transaction, then signals are passed on from one object to another at bit level, and at bit level or maybe at a bus level in case you are using RTL, then you could have a data bus constituting 8 signals or 8 bits. So you could have a bit level or a bus level view of uh, of a transaction. But when you do that, then since transactions are traveling from one or they are kind of passing from one module to another module at bit level, so simulation becomes very slow. So we are going to understand this all these details in more in little bit deeper today when we take on TLM as a concept. So I open today's slides, basic slides. All right. So we'll learn about transaction level modeling. We'll also learn about TLM codes. And after learning about TLM codes, we will open our test case, our test bench, and we will see how TLM ports, basically transmit a transaction from one module to another. So all those details and how different modules are connected, all those details we are going to learn today. But first about what is transaction level modeling about. So going back, we have seen uh, the Moore's law and how verification productivity, though it is increasing, but with respect to design productivity, it's not increasing as quickly, or the rate of increase is not as good as design productivity, and as a result, verification gap is increasing. Earlier, Rocher had given you some numbers, had shared some numbers wherein he said number of design engineers is increasing by a rate of 3 to 4% every year. So there'll be more job opportunities if there is more gap. So the design gap is not as severe as verification gap because job opportunities are increasing only by about 3 to 4% every year when it comes to design domain, associate design domain. But in verification domain, the number of jobs is increasing by approximately 10.4% compounded every year. Okay, so meaning that by it will be like almost the number of verification engineers will be twice as many um, after a gap of 6 years or so. Okay, so every 6 years, number of verification engineers doubles. So we need to see how we can, just give me a second. The top of the slides is slightly getting cut, so I need to take care of that. Just give me a second. All right, now better. All right. So so we need to see how we can have more productive verification and more productive design itself so that we can reduce design and verification gaps. All right. So as SoC size grows, design complexity is also growing exponentially. There is a need to reduce verification gap as well as, so when we talk about TLM is about modeling. So modeling is a design activity as well, though we also need to follow it up with RTL so that, or with behavioral description so that we can implement it in the hardware. But as far as exploration, because when you are going through the activity of designing a chip, for example, one of the initial activity is hardware software partition, or exploring what kind of hardware uh, architecture needs to be used. So all that can be handled through TLM. Transaction level modeling is a way to achieve just that. How to reduce design gap and verification gap. That's about it. So let's see how. So we'll see how simulation technology has developed over the years. So initially we had simulations. We still have SPICE simulation for analog components. And how SPICE simulation works and why it is slow, let's learn that. Current and voltage levels are incrementally computed at each node of the circuit. So we have a transistor level view of the circuit, and so every transistor will have source, will have the different, I don't remember transistor level terminology. So we have source and we have drain, yeah. So we have source and drain, and we have the gate in between. So all three would form different nodes. And when transistors get connected to other transistors, there'll be like with increasing capacitance and with increasing resistance, the connections need to be modeled to as an IR filter rather than one. So each connection will be various nodes because of IR filter kind of characteristic of the connection, because of the capacitance and resistive effects, rather than they being just one node because it's a plain conductor. Because of capacitive and resistive effect, we need to model each connection as well as an IR filter. Okay, so there'll be literally in a billion gate design, there'll be uh, thousands of billions of nodes if we want to do a SPICE simulation, and you won't find a server which will allow you to do a SPICE simulation at that level. Time and precision can be specified. Now, this is important. So when you are going through a SPICE simulation, then at each node, you are incrementally. So this incrementally is in the time domain. So at a particular snapshot, so for example, when a simulation starts, then except for the VDD node where you are giving the where you are supplying power, everything will be connected to ground. So everything will have zero voltage. And just as you start providing power to it and the simulation starts, and you start providing input at the stimulus at the inputs in terms of voltage levels. So at each node, a SPICE simulation will incrementally determine what would be the voltage level. Okay, using models for various components like the transistor itself, or for the resistance and capacitance. Okay, so precision is where you determine whether this activity has to be done at 1 picosecond, or maybe at 0.01 picosecond, or maybe at a nanosecond level. So that's what, no, that's the time precision. Okay, at how you divide the time, how you define, you have the time step and you define the time step like that. And precision is how much you worry about the voltage levels. For example, whether the computation, how many decimal places after the volt, so for example, the voltage could be represented as 1.2 volt, or it could be 1.200 volts. So what's the precision, the voltage precision? Okay, whether it is 0.001 volt or 0.0001 volt. So how precise you want the calculations to be. So why is precision important? Because anyway, a SPICE simulation will be dealing at that level in a computer, so it will have double as a precision. All the floating point numbers can be either the computation can be made in 32-bit level in a computer, or at a 64-bit level, that will be double. Or Intel processors also allow 80-bit precision, which will be which will be another level of precision. So which will be much more accurate than 64-bit, for example. But why is precision important? Why we are just talking in terms of 0.001 volt or 0.1 volt? Because as a simulation progresses, any change in voltage level at a node is going to uh, kind of trigger another cycle of calculation for any node which is connected with this node. So if we use very high precision, the cycles of component, the cycles of computation are going to increase a lot, because with increasing time, uh, the if my voltage precision is by an order of magnitude better than another simulation, then with any increment of time, a lot more nodes will have a different voltage level, and that will trigger computation of spice model for a lot more nodes wherever these nodes are given as input. Okay, so I hope I'm clear there. So I'll repeat. So what spice simulation does is, if there is a change in voltage level, and this change in voltage level will be determined by precision. So if the change in voltage level is more than the voltage precision your spice simulation is configured with, then it is going to trigger another cycle of computation of voltages. So if you are more precise, chances are there'll be with increase in time, it will trigger more and more cycles of computation. And time precision is where the time step is where you say that after every 1 picosecond or 0.01 picosecond, you want to see whether you need to so you calculate with every time step. So increase in number of time steps is obviously going to increase the simulation time, right? And spice simulation is done at transistor level. So the models there are analog in nature, and real or floating point numbers will be used to determine the state of the full circuit. Okay. Now the second is event-based simulation, and event-based simulation is digital in nature. Registers and wires can have only X, Z, or 0 or 1 as values in Verilog. In VHDL, there are many more levels. So you have uh, in Verilog also you can manage that uh, in wires. For example, you have strongly pulled 1 or strongly pulled 0 or weakly pulled, that kind of stuff you can have. But normally for registers, you will only have X, Z, 0 or 1 as a value. An event is a change in value on a reg or a wire. So in spice simulation, the next cycle of computation would be determined by one thing, which will be, so one will be in terms of time, it will be the time step, whatever time step you have configured for the simulation. And in terms of uh, which all components will be uh, in a way, the model will be executed again, or the next cycle of computation will be done again. That will be determined by the voltage precision. So any change in voltage level will kind of trigger another another level of computation. Okay, so in event-based simulations, it will be change in digital voltage levels. So any change from 1 to 0 or vice versa, or it may be from 0 to X, or from X to Z. So all the different combinations or permutations will trigger an event. So any change in value on a reg or a wire, and a reg or wire can have only X, Z, 0 or 1 as values. Any change there in the value will trigger a computation. So we are reducing the number of computations, and we are trying to reduce even the steps of computation. So instead of, every point, every picosecond, as probably it would be the case of SPICE simulation, which has been configured with 1 picosecond as time step. In digital simulation or in event-based simulation, we'll try to reduce the number of events. So we'll see how we do it later on, but that's the point, that you want to reduce number of computations. In a cycle-based simulation, you don't even have events, and event directly maps to a clock cycle. So it's kind of predetermined that computation will be done only on a clock cycle. And all the computation tasks are organized with respect to a clock cycle. So let's see how all these things develop as we move to transaction level modeling. So on the right hand side, I have a very basic diagram where I'm saying, you can compare this diagram with a Moore's machine. You may have learned about Moore's machine and Mealy's machine. So these are different models of state machines in hardware design. So you may compare it with Moore's machine, and as you would have learned, every piece of hardware can be represented as a Moore's machine. All right. So a similar representation I'm using for modeling or for illustrating how a simulation would progress. So any simulation is about hardware state, how hardware state, and the state in a SPICE simulation is the analog state of every node of hardware. In a digital simulation, we model only the connections between different gates, or at RTL level, it will still be different. So we'll talk about it as we progress. But we model the state of hardware in terms of digital voltage levels. So either it's 0, 1, X, or Z. Okay. And so given a state of hardware and given any trigger, so trigger, we'll see how it trigger is different between event-based and cycle-based simulation. So any trigger is going to result in the next computation cycle. So the next computation cycle will, looking at the present state, it will calculate the next state. Okay. So a simulation is an approximate imitation of the operation of a process or system that represents its operation over time. And any hardware is like that. A hardware calculates or hardware progresses in its state uh, over a period of time. So hardware has temporal nature. In context to hardware systems, a simulation involves time incremental evaluation. So incremental evaluation, but it is, I'm also suggesting it's time incremental. So not to be confused as, for example, in SOC design flow, we have incremental refinement. That refinement is nothing but refinement of the model in an incremental fashion. Here it's time incremental evaluation. So we have the same model, but we are running a simulation on this model, and every time we have an increment in time, or we have an event. So time also increments with events. We reevaluate the state of the hardware. That's how simulation will progress. Okay, so in SPICE simulation, this trigger is user defined because we define the user defines the time step, and he also defines the precision, the voltage precision, and that precision will determine whether there is a change in voltage in the next time step or not, and thereby it will determine whether a particular computation has to be done again or not. Okay, an incremental evaluation of the model has to be done or not because the input has changed. So then in event-based simulation, the change would be change in the digital value of various signals. In cycle-based, we predetermine and we say that the changes would happen only at the clock edge. Okay, it won't happen otherwise. So an event is kind of locked with clock edges in a cycle-based simulation. Simulated state is analog voltage values. In cycle-based and event-based, it's always digital values. Simulation speed is very slow, fast, and faster than event-based in the cycle-based simulators. Of these, event-based simulation allows further acceleration. So what happens in cycle-based is, though at RTL level, it may provide you a faster model of simulation or faster type of simulation, but then a cycle-based simulation cannot be used at TLM level, and we will learn why that is so in the coming slides. So this is what a typical SOC design flow is. You would be using functional simulation, which would be RTL level over here at SOC integration level, as well as at custom hardware IP development level. But part of this functional simulation would be your test bench, and that test bench will be working at TLM level to make the test benches work faster. And you will also have TLM simulation, um, which works along with virtual platforms. And this is, this is where, for example, if you work at SOC level and your SOC is really a billion gate design, then even RTL simulation at SOC level will run very slow. So one of the ways to manage that would be that most of the design is taken at TLM level, and then some of the modules come in as RTL modules. Okay, so the environment of those modules would be provided by TLM models of the other modules. So component by component, you may make sure that every RTL works fine, because rest of the simulation, rest of the RTL or rest of the architecture shouldn't be a rest of RTL, because only some of the components are RTL. So the rest of the components, they come in as TLM models, and so therefore the simulation of those components progresses very fast. But inputs to these RTL components are then converted from TLM to the RTL signal level through the BFMs, as we do in case of verification. So the similar way would be applied at SOC design, and so that's a kind of co-simulation environment. So what we are going to learn is why cycle-based simulations are not commonplace these days, because if you are, all these co-simulations will require similar simulators. For example, if TLM is happening in an event-based simulation, then to integrate it with RTL, the RTL also has to be in event-based simulation. So that's why, more or less people have started using event-based simulators everywhere, unless you just want to run RTL simulation at a very high speed, and that will be a cycle-based simulation. So, but normally that's not the flow taken. Normally you'll have event-based simulation, and you'll have TLM simulations and co-simulations, and you'll still have TLM in the test bench part of RTL simulations. So that's how the whole thing will be set up. Finally, after the implementation has been generated, there'll also be gate level simulations, which are even slower than RTL simulations. So we'll take a look at why they are slow and so on. Okay, so cycle-based simulators, though faster, allow simulations only at RTL and behavioral. with limitations. So behavioral cannot be the way behavioral would be with an event-based simulators. So so kind of we are rejecting cycle-based simulators. They are not commonplace. They are not used often these days. Then event-based simulators allow various levels of abstractions, and that's how event-based simulation can, if not done at RTL level, it can be faster than cycle-based simulation. As a result, it is useful. It is a useful simulation methodology for incremental refinement of hardware design, and that's what we are doing here in any SoC design. We incrementally refine from behavioral to RTL to gate level simulations. And behavioral simulations would involve a lot of TLM simulations. So at gate level simulations, now all these are event-based simulations. Gate level, RTL, behavioral, as well as TLM. Precision in a gate level simulation is back annotated, meaning thereby the delays in signal propagation would be back annotated from the layout calculated by extracting the parasitic values of different parasitic and resistor values of different components. Delays will be back annotated at gate level simulation, and so therefore precision is, or I would say rather than precision, I would say time step. It's time precision actually. In any digital in any digital event-based simulation, voltage levels are given. Like voltage would be either 0, X, Z, or 1. Okay, so when I'm talking about precision, it's the time precision. So time precision would be very high because when we back annotate values, then the precision level would be in picoseconds, and then as a result, a lot of computation cycles of simulation would be occurring because every net is changing at a different time because of back annotated timing values. Okay, because resistance and capacitance effects are unique for a given net. And in RTL, it will be cycle accurate. So in RTL, mostly it will be events or precision would be occurring at clock edges. And then there'll be some level of propagation because of the combinatorial part of the simulation. So there will be some level of propagation of those events, but it will be mostly at clock cycles. And in behavioral as well, it will be cycle accurate, but at TLM, there are various levels. So from the next slide onwards, we'll start learning about how TLM allows you to have cycle accurate simulation or approximate simulation. So they are approximately timed simulations. They are approximately cycle accurate, okay, or they are loosely timed. So meaning thereby they are off the actual RTL simulation timings by more than 20%. So approximately timed means by less than 20%, and loosely timed means more than 20%. Speed, gate level will be very, very slow. You can't run a normal test case at on a billion gate level design. So it will be very difficult. You'll be able to do it at module level, but not at full chip level. And then in RTL, speed will be slow at very slow actually at SoC level. At module level, it will be okay for verification, but not good enough for some verification use cases. Behavioral will be fast, and TLM will be very, very fast, extremely fast in some cases. Okay, and then which of them is synthesizable? Gate level is already synthesized, RTL is synthesizable, behavioral limited synthesizability, and TLM is not synthesizable. So TLM in that fashion is only only a level of refinement. So from specifications, you want to create very fast simulations just to explore the design or just to construct the test bench of an RTL design of or for a behavioral design. Okay, and then after this refinement for RTL and for behavioral, we'll have synthesis flow available, which wherein the further refinement is taken care by a flow, and the gate level is already synthesized. So this is typically how typical event-based simulation works. So this flow diagram can be applied to a system C simulation. Verilog simulations will be slightly, will have a more elaborate flow. So in system C or in embedded UVM, this is how a simulation will work. At start of simulation, you will look for runnable processes. For example, in system C, you can have tasks, and with every task, you can specify whether this task will get triggered at the start of simulation or not. Okay, so these are like, so in system C, every task is like an always block, okay, or like an init block, but then you can, not every task will be runnable at the start of simulation. And same is true with embedded UVM. So not every task is runnable at the start of simulation. Only some tasks are marked to be run at start of simulation. Okay, then you will progress, and you will update the channels. Now channels are nothing but at bit level. For example, when you have a register in system Verilog, you have registers, right? So when you declare a variable, you'll say reg 7 is to 0 data. So data is a register. Now, every register can be either assigned through blocking assignment or through non-blocking assignment. So blocking assignment would mean that the register will change its value immediately, while non-blocking assignment will mean that the assignment has been scheduled, and the simulator is going to, or the scheduler is going to change the value at appropriate time. Okay, so if you say A equal to B with a non-blocking assignment in Verilog, and then later on you say B equal to C, okay, or maybe I should say first B equal to C using a non-blocking assignment, and then I say A equal to B using a non-blocking assignment. Now the value of C will be assigned to B, and since I'm using non-blocking assignment, it will not be immediately assigned. It will be scheduled for assignment. And since in the very next statement, I have A equal to B, so the previous value, the new value which has been scheduled will not be invoked. The previous value which is already there will be scheduled for assignment into A. Okay, so we tend to use non-blocking assignments in RTL design. Almost everywhere we have sequential logic. Okay, but what happens is such variables will need to have two sets of data. One the current value of the variable, and then the next value which is scheduled. So the variable becomes slightly like double its size because it needs to have data, and it needs to have the next value of data which would be put on it by the scheduler whenever it is scheduled. Okay, so now therefore that process happens in this part of the scheduler, and then after that we look for the various kinds of events. There are delta events and there are timed events. So every change in value is going to be an immediate event, and if we have change in value after say hash 0, that will be a delta event, and then we'll have timed event where instead of hash 0 we are going to specify what's the delay in a particular component, or what's the delay in assignment of a value from one net to another. So those with some background in RTL will be able to make sense out of it. So immediate events are handled right away. Delta events are handled after update of values on registers, or these registers are called channels in system C. And then only the delta events will be, so wherever we have hash zero details, all those nets will be processed, or all those events will be processed. And finally, uh, if there are no such delays, only then timed notifications will be handled. Okay, so meaning thereby, a separate event queue is created for immediate events and for delta events, and a separate one is created for timed events. And this one is a priority queue, because if the time is less, then that particular event has to be ahead, and if a time is more, then that has to be later. So it's a prioritized queue, usually implemented with binary trees, but that's how it is for timed events. Okay, and delta events, um, all the events will have same priority, so it's just an array of events which will be created. So who creates all these events? The tasks, the computation part of the model, where as it executes, there'll be change in values, and every change in value in RTL would mean an event has happened. So depending on how the value has changed, whether it's a blocking, non-blocking, or it's a timed, you are using hash values for time, for delaying assignments to net values. So depending on how it is getting done, that particular change in value will be registered as an event in one of the queues. And then this whole simulation engine will determine how those events are going to trigger next computation cycles. And thereafter, for example, let's take a small example of um, blocking assignment from signal A to signal B to signal A. So A equal to blocking equal to, so it's blocking in this case, not even non-blocking. So A equal to B, and since value of B is changing, it will result in an immediate event, and this immediate event will be immediately executed, and therefore there'll be more computation happening. In case it's non-blocking, then it will be scheduled for value update, and that schedule, that register value which is getting updated will happen as part of the scheduler algorithm, and it will result, because a register value has been updated, it will result in a notification as well, because value has changed, and this changed value will need to be further propagated through a combinatorial or through a sequential um, module. Okay, any change at input of a gate, or of a flip-flop, is going to result in changes further down the line, and those need to be computed. Okay, so this is how event-based simulations will work. I've mostly taken RTL as context when I've described this working. Now, in gate level simulations, a gate level simulation is the most refined model of the SOC that can be simulated. Parasitics extracted from layout are back annotated as timing delays. So therefore, most of the activity will be in the outermost loop, because every change in value is annotated with extracted delays. So a lot will happen in the outermost loop, and thereby simulation will become very slow. And you do very little. So in gate level simulation, you do very little in computation step, because the gates are the computation happening inside a library gate is very small. For example, a gate may be adding to 2 bits. It may be a full adder or it may be a half adder, and similarly there could be gates who those are for ANDing or ORing, that kind of operations. So computation is very little, while the scheduler is taking most of the time, and that's why simulation will become very slow. So in case of gate level simulation, state is the value on each net, and computation is very simple, and it's the functionality of the components, and trigger is the change in values of each net. So therefore there are a lot many triggers, there are a lot of events which are happening, and the simulation becomes very slow. In RTL simulation, we are able to combine multiple bits together to form buses. For example, a data or an address bus. Now, if you are working with bit vectors, then the event is for that bit vector. Okay, so instead of for every net, it will be event association will be with values of vectors, and there are a lot of values here, and there are a lot of bits combined here. So number of events will decrease. Okay, and computation. So first of all, we need to understand RTL stands for register transfer level. Transfer between flip-flops happen at clock edges. So that's how RTL model is envisaged, that you will be transferring data from one register to another. And here register means a flip-flop. And how you transfer data? Between the transfers, you will invoke some combinatorial logic. So there'll be some computation involved there. So mostly in an RTL simulation, the computation is limited by what can be synthesized, and therefore between two RTL between two sequential blocks of an RTL, there'll be a combinatorial cloud, and that combinatorial cloud will have computation in terms of ANDing, ORing. At the most, there can be addition, subtraction, that kind of stuff. Okay, so computation is still simple. There are still a lot of events, but events got reduced because you are able to group together bits to form buses. And instead of every bit changing independently in a bit vector, the whole value changes. And therefore number of events is reduced. So then the trigger is the simulation cycle typically triggered at a clock edge. So that's what RTL simulation is about. There cannot be any extra data than what is required by the hardware model. So in RTL design, for the sake of computation, you can't keep extra data, for example, local variables and stuff like that. All the variables are static in nature, and hardware means static nature of variables. But for computation, if you want to have recursive functions or you create complex algorithms, then you can have local variables. At RTL level, that's not allowed. Okay, or you can't just keep data as part of a class, and for example, what you do in behavioral simulation or at TLM level, there'll be data which represents hardware. There'll be extra data which doesn't exactly represent hardware, but it allows you flexibility in computation, and computation can be made faster by using those data elements. Each variable in RTL simulation or in gate level simulation is either bit level or bit vector level and has an event associated with it, because change in variable value is going to trigger computation cycles. So there are events associated with every bit. In case of REDs, that's the the data type in Verilog or in system Verilog, and update value is also associated with each variable. So I already explained that why a reg will have two values, the current value and the update value, which may which may happen, which may be scheduled for future. Computation is always performed by always blocks. So there'll be a sensitivity to always blocks. In case of sequential blocks, always blocks, it will be the uh, sensitivity list will have clock there. So computation happens only at clock edges. In case of combinatorial, combinatorial, I would say, blocks. Those combinatorial blocks will have sensitivity list, which will constitute of every input of the combinatorial block, and thereby there'll be a lot of uh, events associated with that input. So that all those events are going to make simulation slow. So the only advantage of RTL, and that's a lot of advantage actually, is where we are able to group bits together to make bit vectors, and that the other advantage is where we use flip-flops, and these flip-flops reduce sensitivity list, and thereby the number of events is going to become smaller, and the simulation is going to become faster. Now we go to behavioral model simulations, and these are, I'm talking about simulations of uh, either system Verilog behavioral models, which can be synthesized, or C, C++, or system C models, which can be synthesized. Okay, now these allow more complex data types, for example, fixed point. Synthesis of many complex mathematical computation is allowed, and therefore call to library, for example, in C, C++, or system C, you are allowed to make call to many math library functions. And data can only be static, because again, even in behavioral model, you are not allowed to keep extra data. Okay, so you are not allowed to keep, for example, you are not allowed dynamically um, allocated memory or dynamically allocated class objects. All that is not allowed. Okay, but let's not focus too much into this, because this is a very special domain which is getting popular with Vivado and with MetaGraphics Catapult tools, and there are tools which other companies have also, uh, like there is a tool by uh, called Forte Design Compiler by Cadence. So all those tools are getting more popular just to reduce the design gap. But these are very domain specific tools and are not used everywhere. So only with data DSP kind of modules, this behavioral model simulation becomes, it is more popular in that domain, in DSP kind of domain. Okay, so and you can have DSP kind of modules in FPGA as well, so it's getting popular there as well. But let's not spend too much time here. Now we come to transaction level modeling. So a transaction level model accomplishes a lot of simulation acceleration by decoupling data state from time. Okay, so now in RTL, for example, I'm not going to talk too much about behavioral, but if we take RTL as reference, then change of data will always trigger an event. In TLM, we decouple those. So we can have data, we can change it, and it's not going to result in another computation cycle. Okay, so now time still needs to be modeled, because in RTL, you don't need explicit events. You can model time by having signals itself. So a wire changes its value after a particular time. So when assigning to a wire, you can give that value of time. So now time is part of data in that sense, that whenever there is going to be change of value, there's going to be an event associated with it. And there you're in RTL or at gate level, you're coupling time and value together. In transaction level modeling, you want to decouple it so you can achieve more computation, because computation will involve change in data values. So you can achieve more computation and yet not trigger a lot of events. So you decouple them. So time in transaction level modeling is modeled generally using abstract events. So event is as a construct itself. So it's allowed in test benches in system Verilog as well, because you want to decouple it with change in values. An event can be explicitly triggered by the model. So you can say, I want to trigger this. So in system Verilog also, there is a special symbol or special operator for triggering an event. In System C or in Embedded UVM, you trigger an event by explicitly triggering it by calling a function. Or you can wait on an event in System Verilog as well as in Embedded UVM or System C. You can just say wait on this event, and that process will start waiting. It will block. Okay, we'll learn more about blocking of processes, etc., in the next few slides. But the major point here is you are decoupling data and time. Then you also decouple data from computation. In RTL or in gate level simulation, every data out there is used for computing the next state. Okay, so the computation, for example, in a combinatorial circuit, computation will be performed on all the input values. Okay, and when you go inside the circuit at AND or OR gate level, then the output of the OR gate forms the input to another gate. So every node in that sense is also connected to other nodes which are input to something else. Okay, so now we want to decouple that in TLM, and we want to say we can have data which is not used explicitly for computation as such. So we can have data which is not like hardware data. It's not static in nature, but it is local variables. We are allowed to use local variables, and those local variables will uh, will in turn be able to do a lot of computation, because there's no event associated with these variables. We need not pass these variables to any other computational task. But so in that sense, what we are trying to do is we are trying to increase what we achieve in a particular task, and we are trying to reduce the amount of processing that is required in the scheduler. So we want to have more getting achieved in a particular computation task, and that's why we decouple it with data, and it may have local variables and may achieve a lot and then create another transaction which gets sent to another task. Okay, and we decouple data and time. So not every time there is a change in data, an event gets triggered. We are able to trigger events based on what we feel is good. So we have decoupled, and therefore we are trying to reduce event processing and trying to reduce the time taken by the scheduler in a simulation cycle. So, and we allow in TLM simulations, we allow flexibility in transaction of data between computation processes. So if there are multiple tasks involved, so we allow flexibility in terms of how the transaction will move from one task to another, and we'll see more of it later. So combined, all these three combined, decoupling of data from state and decoupling of data from computation. I mean, of course, computation will need a computation cycle will need, or a computation task will need a transaction or some data at the input. But then it is able to proceed a lot. It's able to do a lot more by having local variables and having local data, which need not be given to the next computation task. Okay, in RTL, that is necessary. Every time you compute, whatever you have computed, it goes to something else. And at TLM level, we avoid that. So in RTL, your tasks are small. So for example, adding two numbers is a task in RTL. So that's a very small task. And it will, because the output of the adder is going to trigger more processes. So therefore, there'll be a lot of computation cycles happening. In many simulators, like all the EDA vendors are giving simulators, Model Sim, and then you have VCS, or you have simulators from Cadence. So what they do is, in RTL simulations, so for example, you have an adder, and adder is followed by another adder. So they try to reduce computation by merging these adders together as one computation. So that kind of optimization in RTL happens, and therefore you have faster simulation. But you can't go beyond cycle level simulation, because ultimately at the flip-flop edge, you can't have this kind of merging of computation cycles together. Okay, so in TLM we go beyond clock cycle, and we reduce the number of events even beyond. So there won't be an event at every clock cycle. So there'll be an event uh, which will happen only with transaction with a transaction passing from one compute cycle to another compute cycle of the simulation. And that may be multiple clock cycles. It may, in some cases, be thousands of clock cycles. Okay. Okay. So we were somewhere here. Yeah. So RTL simulation only allows only always blocks in a computation construct, and assignment statement is a syntactic sugar for a combinatorial always block. Okay, so I don't want to explain it too much, but RTL can always be written with help of always blocks, and any assignment which is an assignment block in RTL. So there are only two constructs available in an RTL simulation. You can have always blocks, or you can have assign statements. So assign can always be, you may not have assign at all, and you may model an assign statement using an always block. So ultimately, RTL just means always blocks. Okay, so the amount of computation or computation in a simulation is happening through always blocks only. In TLM, instead of always blocks, we can have a TLM task or a method. It's called a method in System C, which runs perpetually. Okay, it does break, but it has perpetuality in its character because it retains its state when it breaks. Okay, so it's in that sense, it's actually like an always block. So it will wait on events, and then when it restarts, the variable values are as if they were there before the wait. So in that sense, a task has to yield. When it waits on an event, it yields. Okay, so you can have multiple tasks working together. One task starts and then it yields when it starts waiting. But it's still, unlike a function, it will retain the values of its variables. So a task has an inherent state. The values of various local variables will not change when a task is activated again. Then you have TLM functions or routines. In System C, these are called TLM functions or basically SC function. And in Embedded UVM, these are called routines. Okay, so they are like software functions. So you invoke them, and at the time of invocation, you pass them data. But then with a task, because a task runs perpetually, you can't pass data to a task in a normal fashion. Okay, because it is running, it keeps running, and in between you want to give it data to crunch or data to process. So, for example, it's in a test bench, it's a sequencer body, and it's a sequence body. Now it will run perpetually. It will have a for loop in there in most of the cases, and because it's generating multiple sequence items, but then it yields when it says start item, it yields because it has pushed the item into FIFO, so it yields. But now it needs more data, so it may need. Uh, so I may not have given the right example in form of a sequence body because sequence body generates data. It doesn't need the data to be transferred from another place, but another, for example, a virtual sequencer will need data, a virtual sequence. So when it needs data, you can't give it data by way of a function call. You need to give it data by some other means because it runs perpetually. It's a function or a task in system Verilog or Verilog runs perpetually. And only at the time of invocation of task, you can give it data. But once it is running, you can't pass it more data. Okay. A function in a TLM simulation can be called by a task or by another function. And while calling the function, you can give it data, or a function can even be triggered by an event. But since a function gets triggered or gets called at the time of calling, you can pass data to it. Okay. So a function cannot yield. So there's no problem in calling a function with data, and that's how you will do it every time. If you have a function and you want to pass it data, then you will pass it as an argument. But if you have a task and you want to pass it data, then you can't pass it as an argument. You can do it only at the beginning of the function, but not later on. At the beginning of the task, but not later on. Okay, so that's the difference between a task and a function. Task will keep running perpetually, but if you want to pass it data or let's say a transaction, then you can't do it by means of a function call. You have to do it in another way. But if it's a function, then you do it as an argument to that function. So let's see how this develops further in case of test benches. But before that, so this is how tasks are, and in case of embedded UVM, you also have something called worker threads. So the worker threads keep working all the time. If you have tasks, the tasks will do the little bit, and then the task will yield, and the control will go back to the scheduler of the simulator. And then the simulator may start the task again, depending on what event the task was waiting for. And if that event triggers, the start gets activated again. Okay, in case of worker threads in embedded UVM, the worker threads are always active. And so we need yet another way to transfer data to worker thread. So a worker thread is free running thread. It's not controlled by event-based simulator. It can only wait for, it cannot wait for a simulation event. A worker thread is actually controlled by the Linux kernel, or if you're running it on Windows, by the Windows kernel. A worker thread may suspend operation by waiting on a semaphore. So it's a system level thread. And when passing data to it, we have to use system level semaphores only in order to pass data to it. So we'll see in code how it is done. We'll see that later, but before that, let's complete our slides on TLM. So despite having a TLM implementation in UVM, system Verilog. So here I'm talking about why system Verilog is slow. Okay, even if you don't have multi-core, if you kind of ignore multi-core, system Verilog doesn't allow you to do multi-core simulations of a test bench. But even if you ignore that fact, system Verilog is still slow compared to system C as well as compared to embedded UVM. So this is what makes it slow. Though at TLM level, system Verilog decouples data from events, but it uses the same data structs or same data constructs that are used in Verilog. So it still uses reads and wires. Now, every read will have an event associated with it. In a typical test bench, you won't use that event, but that doesn't mean that that event goes away. So every time your reg, you will be changing the value of a reg, you will be triggering that event, but nobody is waiting on that event. Okay, so that's what, so there is extra baggage in system Verilog in terms of data types which have events associated with them, and not only event, whenever, and you won't use so many wires in a test bench, you'll use reds, and every red will have an update value. Though in a test bench, you won't use non-blocking assigns. You'll always use, in a test bench, you will always use blocking assigns. The only place in a test bench you will use non-blocking assigns is the BFM, where you are passing the data to the DUT. Okay, but that's not the TLM part of the test bench. So in 80% of the test bench, which is TLM part, you are not using non-blocking assigns. So therefore you don't need regs. You need plain C kind of variables. Okay, so though system Verilog allows you to have bit, byte, short, or int, or a long integer, for example, wherein system Verilog allows you to have only two states, 0 and 1, instead of 0, 1, x, and z. So that makes it a little faster than using 4-state reds, but still it's not sufficient, because even with bit, byte, short, or int, there are update values and there are events as part of the variable, which you are not using, but they are nevertheless there. Okay, and every time you will be changing the value of a variable, the corresponding event, which is part of that register, will be triggered, though nobody is waiting on that. So there is extra processing happening, which is not required. Okay, and that's why system Verilog becomes very slow. So typically, if you are, for example, in a for loop, assigning values uh, to an array which has say 10 million elements, and you are doing some computation there, system Verilog may become slower compared to embedded UVM or compared to system C or C++ by a factor of 20. Okay, and now in case you want to invoke DPI here to make it faster, where you say, okay, let me do the computation part in C or C++, the DPI layer itself will add um, will become a bottleneck. So it will add to computation time because it needs to translate values from registers to the corresponding C types. So it will make it slower. So in effect, system Verilog TLM decouples events from data. Though it does that, the data construct still carries the package of the legacy Verilog types. So then there is a standard in C++, which is also kind of implemented in system Verilog. That standard is called TLM2. TLM2 allows even more freedom from events and therefore from the scheduler, and thereby makes the simulation faster. So by allowing out of order execution of tasks and functions. So see, events are there. So one computation will invoke, in a way invoke by way of triggering an event and passing data to another computation. Um, so events in that session, in that fashion, or even function calls in that fashion have have a nature which is or a character of uh, consequence. An event will trigger a consequence. In TLM, instead of modeling time with respect to events, we still have events, but we want to avoid events as far as possible. So TLM 2 standard allows you to keep data, to keep timing information as data. Okay, and since you are keeping timing information as data at places, things will happen in a way out of order. So because events introduce that concept of consequence. Okay, somebody triggers an event and somebody is waiting on an event, so there is a consequence. The event trigger has a consequence. Now you are modeling uh, this sense of time in TLM2 by making time, by modeling time as data. So the sense of consequence is reduced, and therefore TLM2 allows out of order execution of computation, and therefore it becomes even faster. But then since delays are present only as data points, so in the end uh, a typical TLM2 simulation is not timing accurate. It is off by uh, either less than 20%, which is approximately accurate, or so approximately timed, or more than 20%, which is loosely timed. All right. So now we already saw, because of the nature of different computation constructs, we have functions, we have tasks, and in embedded UVM we also have workers which are free running threads. So now we want to see how to transfer data between those. So that is accomplished by TLM ports. Now TLM ports are derived from the interface segregation principles. So we have a port and an export for each client interaction. Okay, so the interface segregation principle said many client-specific interfaces are better than one general purpose interface. So if you have a class that has several clients, rather than loading the class with the methods that clients need, create a specific interface for each client and multiply. So there is a typo here, which was there when I stated the interface segregation principle. I have copied that typo here as well. So apologies for that. So create specific interface for each client and multiply inherit them into the class. So here, what I mean to say is, for example, you wanted to pass data from one component to another, and you could have done that in case of okay, let me say it after a few slides, because I explain analysis port and stuff like that later. So let me say it there only. So for now, just remember that TLM ports are basically derived from interface segregation principle. All right. So and thereby they introduce, if you are using TLM ports, they introduce reusability. You can make more reusable uh, UVM components if you interface between the components using TLM ports. So this is how a typical TLM port export and its implementation are organized. So a TLM port is an interface, it's the base class. Okay, we gave an object-oriented view of TLM ports. So we gave it here when we are trying to relate it with the interface segregation principle. So we are trying to understand what TLM ports and exports are from the object-oriented perspective. Okay, so when we do that, then we need to understand how TLM ports and exports, how they are architected. So TLM port actually is a base class. TLM port is a base class, and TLM export or a TLM implementation, both export and implementation are extended from the base class. So you see, typically a TLM port, wherever it is getting implemented in the export or in the implementation, actually in both of them. Okay, so when you use TLM port, you are in the upper abstraction layer. You need a service from another component. Okay, so what kind of service you need? Typically, you want you want to either give it a transaction. So you want to say, take this transaction and process it, or you want to get a transaction. So one of these two services. Okay, so you have an interface, which in case of put ports is like put a transaction into it. So it's a virtual function. It's a virtual class. TLM port is a virtual class. So which has a put function, which is a virtual function, and it is implemented by the export and by the implementation. So we'll see why export is there, but export actually delegates the work to an implementation. So export cannot be standalone. Export will always have an implementation, but an implementation by itself can connect to a port. So an implementation will connect to a port via an export, or it can connect directly. Okay, so export in that sense is the strategy pattern. It delegates whatever needs to be done to the implementation. A port always initiates. So in TLM, there is a concept of initiation. So a TLM transaction needs to be initiated. A port always initiates a transaction, and export or implementation executes it. And actually, an export will execute it by delegating it to an implementation. Now, in since the name of the construct is export, you get a feeling that you are exporting a transaction to it. So that feeling needs to go. You need to if that kind of feeling is there, then you need to erase it, because export doesn't stand for, you're not exporting anything. EX in export stands for execution. So it's just that your transaction will get executed on the port. And that transaction could be a put transaction or a get transaction. So you are transferring data, and so you may be uh, pushing data into another component, or you may be pulling data from another component. The only thing about port is whether you are pushing or pulling, it's a base class and it's a virtual function. And if you are pushing, for example, then you are pushing it to another component and through a virtual function. And the guy who gets that transaction will start using it. If you are having a or a get port, then you will request a transaction, and the guy who is connected to it is going to give you that transaction. It's going to push that transaction to you. Now, what you need to see is by way of port, the guy who owns the port will make a function call. The guy who owns an export will never make a function call. It will actually have that function implementation here. Okay, so data exchange in that sense is always happening through function calls only, but a port is the one who makes the function call, and export is the one who executes the function. So whether it's a get function or put function, the export executes it. Okay, now that's a little bit of problem. Like, I'm not able to see your faces, so I'm not able to actually determine which particular thing to emphasize more on. But with that limitation, I'm trying to emphasize whatever needs to be done in order to understand this concept. Okay, so a port is the initiator and the export is the executor. So always think of TLM ports and exports in terms of service request, which is made by upper layer, and service execution or service implementation, where this function is implemented as the lower layer. Now, again, if you see, then I'm talking in terms of function call, a virtual function call, and that function getting actually executed by the service layer, which is the lower layer. So it is sufficient for exchange of data between functions. For exchange of data between tasks, we need to do something more. We'll see how we do that. So a port initiates a transaction, and export executes it, and export delegates transaction execution to an implementation port. So a strategy pattern here, a template pattern here. But if export is involved, then strategy pattern. So if there was no subcomponent, here it's a component A and subcomponent A. Here it is component B, and inside there is a subcomponent B. In case there is no subcomponent, the implementation port will be direct. So that's a template pattern, template method pattern. If there is a subcomponent, since we are delegating the execution of the service request to the subcomponent, it happens through strategy pattern, and that's what export and implementation. That's how they interact there. So let's see. When a TLM port or export, when connection is made, Since these are basically, these are, just give me a second. So I still have 10 minutes to go. I can cover these slides in 10 minutes and then we'll have a break. So when a connection is made, a connection can be made between an export and a port. Okay, and since this is implementation, an export is an export derives from a port. So port is a virtual class, it's an abstract class. Export is implementation of that class. So since this is an implementation, a connection basically means I take this component and I assign it here. So I basically will be taking the export and I'll be saying port equal to export. And that's what the connect function in system in UVM will actually achieve. It will basically assign the export to the port. Port is the base class, export is the derived class. So you can assign the handle of derived class object to the handle here. Okay, that's how connections are made. So you have a function call here, and that function call is implemented in the export. So you just make an assignment. In case of export getting connected to implementation, so export, since it's delegation, it happens by way of composition. So export has a handle of implementation getting assigned into it. So then when a port calls the function, a function call is made on the port, it will get executed in the export, which in turn will delegate it to the implementation which it holds. Okay, so a connection here basically is again an assignment to a subcomponent of export. So an export holds an implementation and it will delegate uh, the, the, the request to the implementation. In case you are connecting a port to a port, there, this is also a virtual, an instance of the virtual base class. This is also an instance of the virtual base class. You need to just make sure that this connection has already happened. So basically, this particular derived class, which is an export or an implementation, has already got instantiated here as the base class, as the base class component here, a base class object here. So once this has already happened, then this can happen. So basically this export or implementation will get assigned to the subcomponent A as well. Okay, but this connection should have happened first. Only after that this connection can happen. Because if this connection hasn't happened, then we are actually getting a null object getting assigned to the base class object here, handle here. So that actually doesn't do anything. And this assignment, if it happens later, then this will not be carried over to this assignment, okay, out here. And that's why the connect phase happens top down rather than bottom up. Okay, because all other phases, build phase, etc., they happen bottom down. Actually, sorry, they happen bottom up, and only the connect phase, it happens top down, because an export, which is actually the implementation, which is actually the concrete class, which is actually the derived class, and therefore there can be an actual object over here. This is abstract class, there can't be an abstract object. So this object gets assigned because this is a base class, so this assignment can happen. So this has to be done on the top level first, and then only this can be taken to the subcomponent. So the top level assignment first, and then you go to the subcomponents, and therefore connect phase has to be top down rather than bottom up. Okay. So port can connect to another port simply by assignment, and export contains an implementation port by way of composition and therefore delegation. And the connection is again made by assignment. So an implementation object is populated inside the export object, and whenever there is a request to export, it basically calls the same function, passes on the same function call to the implementation port. Okay. Slightly complicated here. I believe you will need to look at these slides a couple of times to understand it, and we'll try to understand it in the code examples as well after the break. So blocking and non-blocking ports. So we learned about ports and exports and implementation. We still need to categorize ports as blocking or non-blocking. Non-blocking ports are where there is no event associated with it. We already learned that if we are passing data or a transaction from a function to another function or from a task to a function, then we can pass on the data as an argument to that function. Okay, so now when we do that, there need not be any event associated with it because it's a simple function call, and function call cannot wait on an event. So there is no event involved in non-blocking ports. But on a blocking port, first of all, a blocking port is required if you're passing data to a task or a worker. Okay, since they run perpetually. So, and you are not making a call to a task, you are actually passing data to a task. So a data can be transferred only when a thread is waiting on something. So therefore we have to involve events. So what will happen is the task will start waiting on a port, and only when data becomes available there, the task will become active again. Okay, and this is for a blocking get port. There could be a blocking put port wherein the task will put data on a port and it will get blocked because the port, until and unless it consumes that data, it executes the data, it doesn't let you go. So there is an event involved there, in the sense then when you put, you start waiting for that event, and that event will get triggered only when the execution of that transaction is complete. Okay, so actually these blocking ports and exports, they are the structure has inherent events or semaphores depending on whether you are working um, with uh, with tasks or worker threads in embedded UVM. So in system Verilog UVM, it will always be tasks, not worker threads. So it will always be events. So you have ports and there is an event associated with it. So that's how it will work. We'll go slightly into those details when we start looking at the code, and then you'll understand it better. A blocking port enable uh, a blocking port enables data transaction to or from a thread. This is accomplished by putting data on a port and triggering an event. So inherently, it will actually trigger an event, and that event is going to result in result in the thread which is receiving the transaction or the transaction request actually would be waiting for the transaction, and that thread will become active. So that way. So this is how ports and exports. Now here, something we need to understand. So whenever, so for example, let's take the example of transaction which is passing from the transactor to the driver. Both of them, whether it's all the components on this side of the test bench, that's the stimulus generation side. All the components are actually tasks. Okay, so whenever it's a task, whether a task wants some data or the task wants to push data. So whether it wants to get data or it wants to put data, the task will be the one who will initiate a TLM transaction. So whether it's a get transaction or a put transaction, the driver will be initiating it. If it wants to get a transaction from the transactor, it will initiate it. It will make that call. If it wants to put something, it will again make a call. It will say, put this data. So function call is always initiated by the driver. In a transactor also, it is always initiated by the transactor. Okay, so now how will it happen that transactor initiates a TLM call and the driver fulfills it? So therefore, the driver will have to implement, but driver also is not ready to implement. Driver also says, I'll only have port, not export. This also transactor also only has port, not export, and driver also only has port, not export. So in between, you want to have a FIFO. So when a transactor wants to put a transaction, it will put it into the FIFO. So it will make a request and FIFO is going to fulfill it. When a driver wants a transaction, it will pull it from the FIFO by making a request. Okay. Now you need to understand this concept. Since you are in a task, you can only make a call. You can only call a function. You can't hear because you are already executing something. Your thread of execution is already active. So you can't have a function implementation here in driver. You can only pull. If you want to get a transaction, TLM cannot initiate it and put it in the driver because your driver is perpetually running a task, and there has to the TLM part has to make the transaction available there. So that perpetually running run phase in a driver will need to make a call. TLM cannot make a call to the driver. Driver will make a call, a TLM request. Driver cannot fulfill a request because it's in a task. It can only request, make a request. It can't fulfill. Okay, because fulfillment is always in case of TLM. Fulfillment is always based on executing a function. So there has to be a function which gets executed for fulfillment. That's not the thread of execution in a driver. In a driver, it's a task which is perpetually getting executed, the run phase of the driver. So we can't have export in a driver. We can only have ports inside a driver. So a driver can only make requests. It can't fulfill requests. So all the components on the stimulus generation side, since they are active components, they are all having run phases. So they'll only have ports inside. They'll never have exports inside. Okay, or implementations inside. On the other hand, to make sure a transactor can push a transaction into a driver, there has to be a FIFO in between, because the transactor makes a request and the FIFO executes it, and then driver again makes a request and the FIFO executes it by passing on the data it has received from the transactor to the driver. Okay, between the transactor and driver, there is a special kind of FIFO, which is the sequencer TLM, you know, TLM uh, constructs. So we don't need to go into all that, but it is ultimately a FIFO, but with extra functionality. And between the driver, in case of embedded UVM, between the driver and the BFM, there is again a TLM FIFO, but this TLM FIFO uh, is special in the sense that the driver puts data here, and on the other side of the thread, on the other side of the FIFO, we need to interface with something with Verilog simulation, and the thread of execution of Verilog simulation is not synchronized with the thread of the driver in terms of, because this is a different simulator, this is a different simulator. DOT is under Verilog and this is under embedded UVM. So we have a special kind of TLM FIFO which can interact with the external world. A Verilog simulation is external world for us. On the monitor side, everything is function based rather than task based. So we get a transaction and we put it on an analysis port, and this analysis port, inside a collector you will have an export, or you'll have an implementation port. And in case it's a hierarchical collector with is having a some subcomponents, or in case you are putting the transaction into an environment and that environment holds the collector. So in case that's the stuff, then environment will have an export and collector will have implementation. Otherwise, if it's a direct component to component transaction, so and there is no encapsulation of components with environment or agent kind of constructs, then a port will get connected to implementation port, then this port will get connected to implementation port, and so on. And when you put a transaction, it actually just invokes a function inside the collector. When you put this transaction after say collating different transactions and creating a sequence out of it, you put that transaction over to the monitor, then again you just call the put function and a write function will get invoked inside the monitor, and so on up to the scoreboard. Okay, so here on the monitor side, you won't have FIFOs, you won't have blocking put or get, you actually will be having only non-blocking puts via the analysis puts. Okay, so then the final point, stimulus generation UVM component action is encapsulated in the run phase, which is the task. I already explained that. And since it's a task, all the TLM initiations. So a task cannot fulfill a TLM request because it is already running, and fulfillment is always by way of uh, function execution. On the other hand, the task is already running, so a task only can make request. And on the stimulus generation side, all the TLM ports exports are tasks, and therefore there have to be FIFOs in between. Another purpose of FIFO on the TLM port is on the stimulus generation side is there may be a case where a driver needs multiple transactions, like in case of pipelining. You have a pipeline in AHB, and you have address space or the first transaction getting executed, and data phase or the next transaction getting executed. So you have a pipeline kind of stuff. So there you may need to have multiple transactions available in one go, and you could do it through FIFO. Get another example where you need, because you know FIFO means there is a buffer, there are multiple transactions out there. So another use case of FIFO is in case of multi-layer virtual sequences, and one sequence needs to pass transactions to another sequence, and that will be done through a FIFO, and the last sequence may actually be collating multiple sequences and creating one sequence. For example, it could be multiple application level package payloads getting collated into a TCP packet. Okay, so that kind of scenario. So again, you will need uh, some buffer in the some buffer length in the TLM FIFO, but in most cases you will just keep this TLM FIFO with zero buffer length. So you just get to work with one element. Element gets pushed, and when it is pushed, then uh, after pushing the sequencer, for example, if it has pushed it, then it can't work until it gets pulled by the transactor. Okay, so that's mostly about it. We still have, yeah, that's the last slide. So post lunch, we are going to take a practical look at how connections are made, and we will try to modify one of the test cases. Will introduce uh, um, hierarchy of another component. So we'll introduce maybe an environment or change the hierarchy in some way, and see how exports and implementations are different, and how they relate to each other by way of delegation, and how port connections are made. And then we will also see how the connect phase is always works top down, and thereby it avoids creating you know creating false connections by passing null ports into top level ports. So we'll see that in the code, and thereby we'll get to learn it better. All right. So that's the end of our morning session here, and it's already about 12:15. We get back at 12:45. First, we'll take some questions, and then we'll walk through some of the codes. And after doing this connection kind of stuff on in the lab, we will try to create some new test cases. So that's the next lab exercise, and run those test cases in the SHA3 or in the simple test bench environment that we have for ABSD adder. All right. So that's about it. See you in the next half after 30 minutes. So at 12:45.
Thank you, sir.
Okay, so we also have a quiz at Firoza. Can you tell about the quiz
Yeah.
so that people, for example, if somebody is planning that he'll have lunch post session, so he plans for the quiz as well. So it's
Yeah.
better to have lunch right now than to delay it.
So today from 2:45 to 3:15 we will be having the quiz. So I request you all to please make yourself available. There were few queries related to that. Maybe they are not able to join the session because of their official engagement, but I request you all to please join. We will try to share the link of the quiz on the WhatsApp group also, so that if you are not connected with the system, then also you can, by your mobile also, you can attempt the quiz. So I request you all to please be connected at 2:45. Before that, you close all the browser. Be there. There will be 20 questions. Again, we will be giving 10 minutes of grace time to you all. Please come submit the quiz before 3:15 so that the details are being recorded. So it's an humble request to all of you. Please be connected with us in the second half, and during the quiz time also, please be connected. You will get all the link as early as you have received till date. So please connect and attempt the quiz. Thank you. Thanks a lot, Puneet sir. So we will be connecting back again by 12:45. Yeah, good afternoon, sir.
Good afternoon.
Yeah, so should we start with the
Yeah.
query session?
So we
Yeah.
can quickly take questions first.
Yes, I think so. There are 9 questions from 1057. Like, if the TLM is not synthesizable, then how to map it with the FPGA hardware? The first question.
Okay. So it's not synthesizable, and we won't be mapping it to hardware. Basically, um, we will be mapping only the design to the hardware. So that's what. So I'll take most of the questions. There are not too many. First is in a verification project, how do you partition when you do GLS, RTL, and TLM simulations? All right. So GLS and RTL simulations come later. First part is TLM simulations. So based on your TLM simulation results, you will explore different architectures. All right. So, I mean, when you do TLM simulations, you do for architectural exploration, and TLM simulations, since they also usually have a virtual platform. Either it will be one of the virtual platforms like Vista or virtualizer. Vista is from these people. Vista is from Mentor and Virtualizer is from Synopsys. And Cadence also have an offering in virtual platforms. So one of these virtual platforms you will take, or you can take open virtual platform. So virtual platform basically means you'll be able to execute code and simulation in such a manner that even if you are booting Linux, you will be able to boot it during your simulation. So it will be very fast. And then you will be able to run software on the virtual platform and have the rest of the design, whatever you thought you will be using hardware for. So you'll be architecting in hardware. You create models for that. And as a result, you get a very good idea how fast the whole stuff is going to work at what clock frequency for example if you are exploring whether 2.0 gigahertz processor will be sufficient for this kind of hardware and this kind of software you will be able to get a fair idea within margins of error which will be approximately 10%, so you'll get to know how fast the hardware is going to work, and in case you have some of the portion implemented in software, how fast it is going to run. Okay, so with TLM, you are able to, so once you are satisfied that, okay, this portion I do in hardware and this portion I do in software, you are able to partition the whole thing. And after that, only you start with the RTL, SOC RTL level integration, because till then you don't even know what are the components you will be using for in hardware and what are the components which will be in software. So that way. What is the difference between system Verilog function and task and TLM function and task? Okay, so when I am saying TLM functions and tasks, I mean to say system Verilog or system C. So irrespective of what language you are using, whether it's system C or system Verilog or embedded UVM, irrespective of that, I want to say function and task, and so there is no difference. If you are using system Verilog, then a TLM function will be system Verilog function. If you are using system C, then TLM function is system C function. And if you are using SC function, so to say, and if you are using system C again, then TLM task would be SC method. Okay, and that way. So when I just say TLM function or task, that means we are using tasks or functions from the base language, whether it's system Verilog or system C. How does understanding of working of simulation makes us a better verification engineer? Because it gives you certain sense. I mean, that way, if you read any good book on Verilog, even if it's meant for designers, they'll give you um, how the simulation actually works. So, I mean, it's like how does learning grammar make you a better speaker in English? Because you know how a sentence has to be structured and why it has to be done that way. Similarly, if you learn how a simulator works, you will be able to use it better. That's all. So, by the way, one of the book recommendations is if you want to know Verilog and System Verilog, one of the best books is the book by Thomas. So there is a book on System Verilog by Thomas. Verilog, there used to be a book by Thomas and Murby. So Thomas and Murby are the people who created Verilog. So they were the engineers who created the first Verilog simulator. And then Professor Thomas, he works for a university now. He wrote another book after System Verilog standard came. So he wrote a book on System Verilog. So that's a very good book on Verilog. So all these books will talk about how the simulator works in the first few chapters itself, so that you get a good understanding of it. Sir, what are the different TLM connectivity possible? So as I said, a port may get connected to another port. That is basically you are assigning a port to another port. And of course you do it through the connect function. And then an export could get connected to a port. And when you do that, the export must have an implementation. So port gets connected to export, and export then has an implementation as one of the components inside it. So you must connect the implementation to the export in that case. And or you can have a port connected to implementation directly. So these are the connections possible: port to port, port to export, and in case you do that, then export has a implementation. And similarly, you can even have export to export as well. So export can have another export, and then that export has a implementation. So export is basically a via media for connection of a port to an implementation, in case because an implementation can't connect to another implementation. So they provided another construct that was export, via which you can connect a port to an implementation in case there is some hierarchy involved. So that's it.
Yeah, sir, actually there are a few questions in the question answer section, like you are not sharing the screen. So if you can address that, the question answer session is going on, like they are inquiring that.
All right. So I'll share my screen. Okay. So oops. If I share my screen, then I can't see the question answers. So I'll stop sharing it and I'll look at the question answers. So I'm going into the question answer section. So that's what. Is this presentation uploaded on the drive? I will be uploading it. I mean, I'll be sending it to Firozaji and she'll upload it. Why we go for service request and service provision? You know, that's only a UVM terminology. Like a TLM, you initiate a TLM request and then somebody provides it. So this is a TLM terminology. And I don't understand why you are asking. I mean, this happens this way because we are actually using object-oriented programming, and there is a base class function which gets implemented. So that way. So then the TLM terminology is that the base class or the port initiates a transaction request and the implementation port fulfills it. That's all. So why we can't put a transaction directly? Why do we need TLM? Okay. A TLM again is just a standard. I mean, how do you put a transaction directly? First of all, if a transaction, so I took the various permutations and combinations or the various use cases, the computation in any simulation model, it's either done by a function or a task. So I'm not going into embedded UVM right now, just for sake of understanding, let's keep it simple. So I'm not going into worker threads. So it's either has to be a function or a task. So now a function cannot call a task, right? A function can call only functions. And a task can call functions, or a task needs to interact with another task. So in that sense, in case we are going to call a function, so there are ultimately only two categories. Either we have some data and this data needs to be given to a function for the next computation cycle in the simulation model. Okay. Now, if it needs to be given to a function, then obviously we can just call that function and be done with it. Or the other is if it needs to be given to a task. If it needs to be given to a task, then we can't call the task. We need to somehow transfer the data to the task. And that is done by the blocking ports. Now, how the blocking ports will manage it is, first of all, we can't transfer data to a task. The task has to initiate. The task has to say, I need data, then another task or another function will provide that data. Okay, so how will that happen is the task will make a request and that request will need to get fulfilled by somebody. Now, since we are talking, when we start talking in terms of task getting data from another task, so there you need some sort of interface between the tasks, and that is provided by TLM FIFOs. Okay, now all this, I mean, what exactly, how exactly, if I put this question, so your question is, why do we need TLM? Why can't we put it directly? So my question is there a way of doing it directly between two tasks, for example? What would be the way? So you have to go through a FIFO if you have two tasks, and so TLM provides that FIFO. On the other hand, if it is like the simple case where a function is passing a transaction to another function, so there is no task involved. Now, so your question will then translate to, why can't we call that another function directly? Why we need to go through TLM ports? So there I would say we do that for sake of reusability, because if I have one module A, which is having a function, and then there is another module. Now these modules are basically class objects. So the other class object has another function and I need to pass data to the other class object. I can simply call that class object, but then it will not be reusable. Okay, because the name of that function will be non-standardized. There's no name, right? And then if I do that, there'll be a dependency. To resolve this dependency of module B on module A, I go through the dependency inversion principle. That means I need to create a virtual base class and then have the implementation in module B. Okay, so we go through dependency inversion principle, and then we go through the interface segregation principle because of sake of reusability. So as we do that, that becomes TLM. And therefore, I mean, if you don't use TLM, you do it yourself, then you will be reinventing the cycle, reinventing the wheel. So from the fundamentals, we need to make sure there is no dependency, and we need to make sure that we segregate the interfaces. Then only we can have a solution which is reusable. See, if you don't do all this, still the things will work. just that they'll be rigid, they will not be reusable, they'll be fragile, and so on. Okay, so you want to avoid that, and when you avoid that, you use the object-oriented principles. When you use the object-oriented principles, then why not use a standard, because standard makes it even more reusable. All right, so then there is a question. Is export used in TLM same like which can send data to its parent class? No. A port gets connected to export or implementation. Port is the initiator, and initiator is either a function or a task, but fulfillment has to be done by a function. Okay. So by actually an export has a connection with, or implementation has a connection with a function. So as I said, don't think export as, we are exporting some material or we are importing some material from another country, for example. So export is not for exporting a transaction. Export is the word ex here is for executing. Okay, so a port where a transaction request gets executed. Now a transaction request, not a transaction. So we are having ports and exports for exchange of transactions. Port to create or to initialize a request, and it can be a GET request or a PUT request. Export for fulfilling that request. So in case it's a GET request, then export by involving an implementation port will fulfill that. That means send data to the service request, to the place where a service request originated from. Or in case it's a PUT request, then the initiator is passing a transaction, and export actually delegates to the implementation port, so therefore calls a function which consumes this transaction, which executes the transaction. Okay, so just again, EX stands for execution. So execution means fulfillment of the request. Sir, we can use mailbox for communication. Why we go specifically to TLM? Okay, a good question. Actually, if you look inside TLM ports and exports, then inside the FIFO-based ports and exports, you will see there is a mailbox, and mailbox is the construct which actually implements a FIFO-based TLM communication channel. Okay, so now the question therefore remains: why do we have a wrapper over it? And on the other hand, all the analysis ports, etc., that we use on the monitor side, they don't need a FIFO. They don't need a mailbox as well. So we just execute the transaction using port export over there by broadcasting the transaction on the analysis ports. Okay, so on monitor side, we don't need it. We don't need a mailbox. On the generator side or on the stimulus generator side, we need a mailbox, and it is actually present inside the TLM FIFO. Now, why have the TLM FIFO? Because if I leave it to you, then you will create a mailbox and you will name it something. Okay, you will name it something, and then the functions that you use for communicating, or the method that the kind of architecture you are going to make will not be following any standards. So just to have some naming convention and everything, there is a TLM over it, and also because TLM has been a standard in the System C world. So just to make sure that we don't become system Verilog specific, there are TLM wrappers on top of mailboxes, and they provide some slightly more services on top of, like standardizations of the function names for putting thing into a mailbox. So the mailbox will have system Verilog specific function names, and TLM will follow the TLM methodology. So there'll be TLM specific function names. So all those function names will be slightly different. So it's just a methodology. So there is not much that TLM layer adds to it. We are just following a methodology. Is TLM FIFO a class in embedded UVM, just like system Verilog? Yes, it's a class. So you have all the classes that are there in system Verilog. They're all there in embedded UVM as well. Then screen is not visible because we are going through question answer session, and I can't look at the questions in case I share my screen. What's the difference between TLM FIFO versus queue versus mailbox versus semaphore? All right. So TLM FIFO is a mailbox. Inside it, it's a mailbox. Difference between mailbox and queue is queue doesn't have an event associated with it. Mailbox has an event associated with it. So when you try getting a transaction from a mailbox, for example, and mailbox is empty, so it will be blocking. So until somebody puts another thread puts a transaction into the mailbox, my call will get blocked. Okay, so therefore it has events associated. You can wait on a mailbox, so to say. Queue is a plain data structure, so you can't, in case you are trying to access an empty queue, you will get an error, but you won't wait for, the queue will not have a construct to wait for somebody, uh, to wait till the time somebody puts a value in the queue. But that can happen only with a mailbox, and TLM FIFO internally is just a mailbox. Semaphore is slightly different because mailboxes wait on events. Okay, semaphore, if you are having communication um, between two operating system threads, so these are not simulator threads. So you are having one thread which may belong to the simulator, but you have another thread which doesn't follow, which is not synchronized with the simulator. It doesn't know what events are. So then you need to, because you are relying then on the operating system. So that's when you lock with semaphores instead of locking with events. All right, where to use it specifically? So I don't get that question. Where to use a semaphore specifically, or use all of them specifically? If you are talking about all of them, then TLM FIFO, which basically is a mailbox. So you don't use mailbox directly in UVM methodology. You use TLM FIFOs. So in UVM, you use TLM FIFOs mainly on the stimulus generator side, or anywhere where you need to make communication between two components, and the component which is executing, or actually the components involve, not execute. So it's not about executing, but the components that, or the components who need to exchange data, they are doing it inside run phases, and therefore you can't do it through a function call directly, and you have to do it through putting and getting data over FIFO. Okay, so TLM FIFOs wherever communication needs to happen between two tasks, and run phases are all tasks. Queue, when you need to store data, but it's happening, the function, the TLM transaction is happening via normal TLM ports and exports. So there is no tasks involved. Everything is through function calls. Okay, so in case there is a task, then TLM FIFO to store data to store data in that intermediate level. Okay, and Q when you want to store data in TLM, but uh, then you can't use TLM FIFOs because, or don't want to use TLM FIFOs because it's happening um, in a function to function call manner, so there is no timing involved. And in the execution of the transaction, if you want to store it on a queue. Mailboxes you never use because you use TLM FIFOs. And semaphore, if you want to communicate from a simulation to the external world, so that's where you use semaphores. So we'll see some semaphore example. Um, Semaphore example today also, because we will be communicating from embedded UVM to the simulator. So that's done through a semaphore based component. Okay, so any other questions you can ask right now, otherwise I'll move on to the code. Okay, so there is another question, sir. Is export used in TLM the same? Okay, that has been handled. So that was a question. That was a repeat question. All right. So once more, TLM is a standard, and TLM implements two object-oriented design principles. One is dependency inversion principle, so that if you are communicating between two modules or two blocks in a model, in a TLM model or in a simulation model, then when you are communicating, then you shouldn't have dependency on one module to another. Okay, because you want to have a lot of reusability there. As I said, for example, in a TLM simulation, you may want to remove one of the blocks and instead have an RTL implementation of the block in that place. So that kind of reusability, that you are able to plug in one module, one implementation of the module, and take out another. Okay, so take out TLM implementation and plug in RTL implementation. So when you do that, the wrapper around RTL will follow TLM protocol, and it will be the same standard everywhere, and therefore this kind of plugging into the top level TLM environment will become possible. So similarly, if you are creating a virtual platform and therein you require, say, USB module, then if you are taking ULM, this TLM model from one vendor or another, so it's kind of you are creating IP level reusability in very high abstraction simulation. So that's where TLM is a standard. Okay, so and that's why we don't use mailboxes directly, because if we start using mailboxes directly, then we are kind of making reuse more difficult, because a system will lock, say, a system C module you want to put into the same place where your reference model is, and reference model is also connected via TLM interfaces. So that kind of reuse will require more manual effort. And so dependency inversion principle to make the dependencies go away by way of introducing abstractions, and interface segregation principle, because we want to have a separate interface for every client that we are dealing with. So TLM, therefore, using these two principles enables reuse and makes go of rigidity and fragility. All right. So now I share my screen first, and then I open VNC. All right. So then I invoke a terminal. I still need to make the font size bigger. So after configuring, I invoke the terminal again. All right. And now I put the path. I will not be using this beta version today because of some issues I faced. So I'll make a release tomorrow that you can use after you download it, because I anyway have to make a release for making making ARM binaries, for compiling ARM binaries. I only have to make the release. So I'll make a release tomorrow, which you will be able to use. But there was a small bug in this release which I have fixed, but I'll have to use the fixed version. So I'm using it from another area, EUVM, not beta. So here I'll actually use it from LTC 121 bin. So I have a development version here. I'll be using from here. Okay. And then I need to go to work and to the workshop. And therein I go into the AVMM SHA3. Okay. Now I go to the simulation directory and I say make clean, and then I look at what files are there. I'll clean those as well. So I'll remove avl.log and avmm log.text and the compile log, and then I'll say make. All right. So then I say make run. Okay, I had changed the test case. So now the test case is very small. It just executes 4 transactions. So let's go over what are the changes in the test case. Okay, so hope you are able to see my screen. So from within Emacs, if I'm using Emacs, and obviously I'm using Git because I downloaded stuff from GitHub. So what is possible is I can say meta x market happened. Something killed my image, so I'll have to launch it again. So I'm able to say escape x market status. So if you are using Git, and of course you are using, and if you have done any local changes, then market status will tell you what are the files which are extra. I mean, which weren't there when you downloaded from GitHub. So these are the files which are extra. Okay. So these got created because we compiled and ran a simulation. And then it also says of the downloaded files, if there are files which have been changed, then what are those files? So we see a change in make file, and we see a change in avmm.sha3.d, which is basically our UVM test bench. So let's go through the changes. So within Emacs, I'm able to say what are my unstaged changes on this file. So unstaged means it hasn't been checked in for, it hasn't been staged for checking in into Git. So you can learn more about Git from the web or from a book, but I'll be using these utilities. So then I get to see this is one of the changes. So when my original make file, which is on the top half of the window, it doesn't have verbosity specified. It has verbosity specified, but that's after a comment. So anything after hash in in the in a Linux shell would mean this portion is commented out. But in my latest file, I'm saying I don't want to see many messages, so verbosity is none. And then the next change, there is no other change. Now we look at the change in the test bench. Same way, using Emacs commands, I'm able to look at the changes. So the first change is I have introduced another sequence item, and this sequence item is an empty sequence item. So instead of phrase getting a random length, I'm saying the length is less than equal to 0, and effectively it will mean it is 0 because length is always a positive number, always a 0 or a positive number, or I can make it equal to 0. Okay, so this is the first change I made. So I extended the sequence item SHA3 sequence item class, and my sequence item class is the topmost abstraction. From this, using virtual sequence, I create the two more layers, and then I drive the data into the DUT. Now, this is the level, like if this is the sequence level where if I were using software, then this is the transaction item I would have been passing to the software. So this is the topmost sequence layer. And then I introduced another variable into the original sequence item, and that variable is rate. Okay, now what I'm trying to do, let me open the slides, then I'll be able to explain what I'm trying to do. So I'm opening day 3 slides. Okay, so first I'm going through the lab where I want to write a couple of more test cases just to test this whole thing more rigorously. All right. So here, if you see the SHA3 specification, so there were different modes in which SHA3 works. There is 224 mode and 256, 384, as well as 512-bit mode. All right. So now, as we talked about it earlier, the higher the number of bits in a mode, like 512 is the highest number of bits. So that is the most secure SHA3 encryption. And that will take more time because the rate of transfer of data from software to hardware will be slower. Now, how that rate works is you have 200 bytes of data, of which only certain amount of bytes or certain number of bytes can be fed in. The rest of the frame has to be 0. And the rest of the frame is decided by twice the number of the bytes in basically the bytes in an encryption mode. For example, in 512 is 64 bytes. So the output will be 64 bytes. Okay. So the input correspondingly needs to have size into 2. So in this case, 128 bytes empty. So we'll be able to transfer to the DUT only 72 bytes in one frame. Rest of the frame needs to be empty. So that's how SHA-3 communication or SHA-3 interface for us is. Ultimately, the base level protocol that we are following is Avalon memory mapped bus, but this is about rate, like how many bytes I can give to my DUT in a given frame. Okay, so now this rate variable I'm introducing in my code as a random variable. All right, so there is already outsize, and obviously outsize and rate, they'll be related. So what's the relation? Rate, the relation is rate is equal to 200 minus twice outsize divided by 8. So we have decided to use rate as number of bytes, and 200, so this formula I'm putting in constraints, meaning that by size will be the output size, and it will be divided by 8 because output size we generally take in terms of bits, and twice that. So this is what I put here, twice outsize divided by 8. Now I'm not putting outsize divided by 4, I'm putting twice outsize divided by 8 because a code should be readable. I mean, if I put divide by 4 over there, then I need to put a comment there why I'm doing it that way. So instead of doing it that way, I put 2 into outsize divided by 8. Then I want to test a corner case, and that corner case is that my phrase length is the original input that I'm giving in. My phrase length divided by rate, or actually, yeah, divided by rate, and the remainder therefore is 0. So in case I'm using 512 encryption, this corner case would mean that I am giving I'm giving phrase which can be handled in complete frames, so there won't be any extra bits. Okay, so what will happen in such a case is, so one of the corner cases obviously is that phrase length is 0, and therefore if we divide it by rate, the remainder will be 0. So one of the cases which fulfills this constraint is that the phrase length is 0. The other could be I have exactly 72 bytes, and my mode is 512. Or if my mode is 256, then I have exactly 136 bytes. Okay, so therefore, if you look at this frame, then I'm able to fit in my data exactly in this frame, in the first frame itself. And the second frame will be all empty. It will still go because I need to still give these escape characters. So the first byte will be 06 and the last byte will be 80. Okay, so my assumption is there'll be 2 frames in such a case, and the second frame will be completely empty only with the escape characters. Only the first frame will have data. Okay, so that's the way an empty frame will be, empty phrase will be given. In the empty phrase there will be nothing. The first frame will not be there, and the second frame will have 6 and 8 0. That's it. And in case I have uh, the phrase length which can be divided by the rate directly, then there'll be some frames which will have data depending on how many frames I can fit data in, and the last frame will be completely empty. 0, 6 and 8, 0 should go there. Okay. Then we still have a corner case where we want to see what will happen if my rate is, for example, if I not my rate, if my phrase length is rate minus 1. I mean remainder from dividing the phrase length with the rate. If I divide phrase length by rate, the remainder should be rate minus 1. That will be another corner case. Okay, so these are the two corner cases I want to simulate. So obviously, I want to put this kind of constraint. I'll remove the first constraint. I put it for debugging. So still there needs to be a constraint on the length. So let's put a very big number. So now I have a test case where I can run this test case and find out if things work. Okay. So the same test bench I have modified. I made some changes and then I want to run again. So what are the changes? These places I've changed constraints, and then I'm printing my request just to make sure that my constraints hold. Then the last changes where I'm saying I'm again printing something for debug, and the last one where instead of 100 packets, I just test for 4 packets. Yeah. Okay. So let me run this test case. So I say make and then I say make run. It will quickly finish because there are only four frames. All right. So now first thing I can do is I can say make minus n run, and instead of none, I give the verbosity as debug. Okay, debug probably is too much because it's printing or dumping into logs all the EVST transactions. I don't want that level, so I say medium. All right, so I see four clean transactions, and by the way, this one is matching, and as you can see for this transaction, it's a right transaction. So then we see there are 728 elements in the phrase, and we see outsize is 32. So that would mean frame rate is 32 into 264, and 200 minus 64, that would be 136. So 136, and this is 728. So if I divide 728 by 136, okay, so 6, it doesn't seem to match. Let's look at another one first. Then. So again, it's 32, rate is, no, there seems to be a problem here. The rate is 32, and outsize is also, no, sorry. So I made a mistake here. These are the rate is, the size is not 32, the size is 384. Actually, this is the number of bits in the size, so it shouldn't be taken as 32. Okay, so rate is 68 actually. So this is 384. 384 would mean 4 and 384 divided by 8. So that would mean 48, right? 4, 4 and then 8, yeah, 48. So my out size is 48. 48 into 2 is 196. So I need to have 104, and this is hex value. So this also converts to 104. So my rate is actually 104. And if I multiply 104 by 7, I get 728. So phrase size is correctly is actually adhering to the constraints that I have specified. So it's 728. Okay. Now another place we check. So 48, that's our rate. So 16 into 4 plus, so this comes to 72, and this is 512. So that matches again. And if I divide um, 504 by 72, I again get 7 frames. Okay. So, but that also matches correctly. And this is again 104, and here it's 416. So 4 frames. All right. And then finally this one, this is again 104, and this is 728 again. So 7 frames again. So 7 frames in 3 cases and 4 frames in 1 case. All right. Now, as you can see, everywhere it's matched. Okay. So now let's take a look at the waveforms. All right. So it's like over here that my frame would have ended. So if I look at what's happening in the end, then the addresses invoked over here, right? So I'm making some writes on those. So this is my data. This is my write data. And I bring it close to the address. And these are all write transactions. All right. So in the end, I'm accessing 08 on address. And that would mostly be because I want to put that in it and next kind of stuff there. Okay, I need to put some values on the control registers. So I'm putting 0, 0, 2, and 0, 0. I want to say in it, and then, or maybe it's not in it, it's next. And then I want to just give it as a pulse. So I erase that value. Okay. And then if you go before that, so somewhere you will see 80, 80 over here. So that's the frame. So you wanted to have 80 and 06 as well. So 80 comes here, and then somewhere we need to look for 06. All right. And from 06 onwards to 80, this is where we are implementing Just give me a second. This is where we are implementing this part of the stuff. So this will be fully all zeros, just that it will start with 06 and end with 08. Then we also need to fill all these values with zeros, and that's what is happening before that. And then we finally have some data somewhere. Okay, so this is how our test input is going. Now we again modify it in such a way that we want to see, instead of having this all, this is one corner case where we could fill in data into frames, and then the last frame was completely empty. Now we want to do it in such a way that we fill in data and there is 1 byte remaining, and 80 and 06, they overlap to create 86 as the escape character. Okay, so let's do it. So what we do is, so now in this case, we change the constraint in such a way that we put phrase length my percent rate equal to rate minus 1. All right, we save this, we go back and compile. And then we run it. Okay, so still no errors. And then we run it with verbosity set to medium. And then we look at what has been dumped in the log file. So we see over here, the rate is 90. That would mean, because it's 224 mode, so the rate is high, and 90 would mean 144. And we see 431 here. That is one less than 432. Okay, so if we divide 432 with 144, we get exactly 3 frames. So 1 byte is with 1 byte to go, and that byte is the one which we want it to fill with 86. All right, and then this is a mode. This is a rate of 88, and that's 256 mode. That would mean 136 bytes in one frame. And had it been 680, that would mean 5 frames, so one less than that. So our constraint is getting fulfilled. And this is another case. 136, twice of that is 272 minus 1. 48, this is 512 Wala mode. And so 48 would mean 8 plus 6, 72 bytes in one frame. And 72, when you divide 504 with 72, you get 7 frames. So just 1 byte less than that. So now if we look at the waveforms, just give me a second. If we look at the waveforms, we want to see that one place it's exactly the place where it fills in the escape characters or the delimiters. It's actually putting 86 over there. So that would be somewhere near the end of the complete cycle. And we zoom on that, zoom on this area. So in the end, I see um, write data as 0, 2, just to create that pulse. And then I don't see it 86 here, 86, the last byte before that. There is 86, 86022 because a word would have many other bytes. So you have the 86 coming in the, so this is um, probably this would be little endian, so that this is coming in the end, actually in the, so the most significant bit is coming later in the stimulus. So that would be little endian. No, uh, depends on how you interpret the stream, whether the stream itself is, uh, yeah, so stream itself is lower addresses first, and therefore lower addresses get lower data and big addresses get big data. So that's how it is. So we do see 86 in one of the bytes, and then looking at the other frame out here. So in the towards the end, you do see 86 here, 86 again, right? So this is our delimiter. And then the last frame, or there are two more frames, so we can take take a look at the last frame, and again we'll see somewhere towards the end there is 86. Okay, so that's how it operates. So using constraints, we were able to modify our test bench to create a test case that works in this way. Now, one option obviously is that I I create multiple copies of my test bench because I modified the test bench. So one option is I create multiple copies of the test bench. So here is the test bench. So I say copy AVMMD, okay, and I copy it to create AVMM test1.d, right? So here my first test, which is completely randomized. I don't put many constraints. So that could be my first test case. So I create that. Then I start putting constraints and I keep creating copies. And then whichever test I want to run, I'll use that copy. So if I do that, obviously there is going to be a lot of repeat code. So later, if I see there is a bug in one of my test bench components, or I want to add another monitor, I'll have to go into every file out there because I made copies and I have to modify each one of them. So there has to be a better way. So I don't create copies. What I do is I open the test case and test bench actually, and so the idea is to use that idiom, don't repeat yourself, and um, to use the object oriented design principle, that is the open close principle. So the not the open close, yeah, open close principle. So it says don't modify your code, extend it. Okay, so instead of modification, what I do is I take this class and I extend it. So I take this class, sorry. So instead of modifying it, I need to extend it. So I had introduced rate, which I shouldn't, and I had introduced these two components, these two constraints over here, which again I shouldn't have, because I need to, instead of modifying the base class, I need to extend it. All right, so this gives me the original test case, test bench, and now I create another class. I create class SHA3 sequence item. Now here will be one where the frames are exactly, uh, you have phrase length which exactly fits into the frame, the rate. Okay, so I can create a name saying remainder 0. Okay, and then it extends SHA3 item, and then I add constraints over it. So that's one way to go. I add constraints, and when adding constraints, I need to mix in, and then these two lines I need to copy. Today, this Q needs to be with the start of brace. Okay, and then these two lines, and I uncomment these two lines, and then hand out this constraint, and I put a name over here for this constraint. I put it as remainder 0. This is the constraint. Okay, now in my test case, instead of using SHA3 sequence item, I'll use SHA3 sequence item remainder 0. So where I have that not equal to 4, that is not equal to 4. Yeah, this place. So instead of that, I can retain not equal to 4. But then this test case, SHA3 ABL sequence. No, not this one, sorry. There would be another place where I have not equal to 4. Yeah, this place. So instead of creating SHA3 sequence, okay, sorry. SHA3 sequence, and that sequence is getting, so I'll have to go and find where the sequence is. So this sequence, okay, now this sequence is taking SHA3 sequence item as a parameter. So I need to modify that. I need to say it takes T as a parameter. All right, and then I need to um, go ahead and I need to put a condition over here that if this is embedded UVM specific, I may not put this condition, but this is better to put. I mean, it makes code more readable, as well as it makes sure that nothing can go wrong with it later on. So I need to put T is the derivative of type. But what's happening here? I didn't. I need to put SHA3 sequence item. Okay, so T is derived from SHA3 sequence item, and then only it will work. Okay, so now obviously if I'm giving T over here, then I need to give T here as well, because T needs to get value from somewhere. Okay, so now I need to go back, go to the place where I was creating that test case. And here I need to give, yeah, SHA3 sequence item, so that now like I'm still working where on the place where if I just need to rerun the previous test again without the sequence, without the extra constraints, so that should happen. So let's work it out with parameterized stuff first, and then we'll see. So SHA3 sequence takes the sequence item as a parameter now, and this parameter will be what kind of sequence item it is. Okay, so let's compile it again. It should run with completely randomized stuff. Okay, so some errors, we need to check what the errors are. So first it says constructor void, this is not callable of arguments string. Object defines, so some arbit error. Why? Let me check where this error is coming from. This is because of meta build, meta, and where it comes from is here. Registry SHA3 sequence item. Okay, so this error is because we created another class and we failed to give a constructor in that class. So we have this class with remainder 0, but it doesn't have this constructor, and therefore the registry of the class is failing into the registry of the class into the factory registration, that's failing. Okay, so we fixed it. Again we say make. Again there is an error, and where is the error coming from now? Object utils. So this is because of the same class. So for the time being, let me so what's the problem here? I don't have, I haven't declared rate anywhere, so that's the problem. So let me just say rand uint rate here. Okay, now things should be fine. Okay, so now if I run, it's just a randomized test case. Now if I want to modify it, and in the test case that we are creating, and that's where is the test case in the end. Okay, so instead of creating this test case this way, we create another one and name it randomized remainder 0. Okay, and in place of this sequence item, I provide it with the other sequence item. This is becoming a little bit more complicated than I thought it would be, primarily because because of parameterized classes and because of virtual sequencer and stuff like that. Had it been a single sequencer, then I would have, had it not been virtual sequencer getting involved, had it been a single sequence, then I may have given, because this is not the sequence, this is the next level of sequence. But had it been a simple sequence, I would have given randomized width, and that then I could have added a constraint over here, and thereby uh, instead of having another class. But that uh, may not be completely okay, because I'm also introducing another random variable. With randomized width, you can't introduce another variable. So probably this only is the way to go. And then instead of, because I'm using randomized parameterized classes, so parameterized classes cannot be um, created through a factory. So I need to give another wrapper to that class, and that's what I do. And that should create this test case named random test remainder 0. So now if I run my, so first I need to compile. Okay, and then I can run either the one with remainder 0 or without the one. So both should work. So random test or random test remainder 0. So this now, as we go back, we will see the particular constraint holds. With 2 to 4, the rate is, actually it hasn't put the rate still. So there is some problem. It's remainder 0, and we have raise outsize. Oh, so we haven't put that attribute on rate. So I'll have to open the test case again. So see, I haven't, when I created this class, I put the rand attribute, but I didn't put the default attribute. So I need to put the default attribute here as well. Here, I put the default attribute. Only then it will start printing the value of name. So I compile once more. And actually, as I do that, it's much better, because rate is, I need to see the decimal value for rate. By default, it will show hexadecimal value. So I put another attribute at the rate UVM deck, so that the value displayed is hexadecimal, in decimal rather than hexadecimal. Okay, so I put that. Now our rate will become visible. So you see rate at the end, and the value is not having 0x as prefix. So it's a decimal value. And on the top, phrase is having 431. So did I code for remainder 0 or remainder -1? So we'll need to see. So I have -1 over, rate -1 over here. So it's not remainder 1, but you get the idea, like that's what you see here there, therefore. Okay, that's what you see, that um, I've created a new test case and have added constraints and this way. So now it required me to work this much, and only then I was able to do this test case. An alternative is to use factory pattern and have factory overrides, and thereby create new test cases using a permutation and combination. So whenever a sequence item is created, instead of sequence item, I can override the factory and make sure that a derived class is created. Now, I don't think there is time for that right now. We can take that example on Wednesday. For now, what I'll do is I'll um, focus on TLM connectivity so that we get a fair idea of how to basically create components and connect the same via the connect phase. Okay, so let's go through that, and that will take some time. And on Wednesday, I'll complete this example and I'll show how a factory can be invoked to run a test case with the factory override of one of the classes. Now, the same thing we have done manually, but doing it manually required a lot of recoding that can be avoided by factory overrides. Okay, now coming back to the TLM ports and exports. So we see that there won't be anything in sequences and sequence items, because sequences and sequence items are data types, they are not component types, and um, ports are associated with components. Okay, so we have this starting here, we have components. Before this, we have sequence items and sequences. Starting here, we have sequencer, and sequencer, um, all the ports exports are hidden in the base class, so we don't uh, have a neat way of looking at the base class, so we avoid that. Then there is an agent, and agent also doesn't have any ports or exports. And then we have sequence item again and sequence again, so we have very few components. And then there is a sequencer again, and sequencer has a port now, sequence item pull port. And this is now because it's a virtual sequence, so there's a port here. Okay, UVM sequence item pull port, and there is a port. Okay, and one thing we need to make sure is that anytime we have ports, we build them. Ports are components. Ports as well as exports, they are all components. Okay, just like in system Verilog, if you want to have analogy, then in system Verilog, a virtual interface is like a port, and the real interface is like an export or the implementation. Okay, so when you have a virtual interface, then it's like a pointer, and and in UVM, the actual port is like a pointer because it needs to be assigned something. So now this SHA3 get port, this needs to go somewhere, and this is how it's getting connected. In the SHA3 environment, from inside agent and from inside sequencer, I'm getting this port. So I have a path to this port, and I'm connecting it to phrase agent that's on the that's where my virtual sequences, and inside the sequencer, I have a sequence item export. Okay, so now here, sequence item export. Why don't I see it? Okay, sequence item export is actually the default port. of the sequencer, so we don't see it. So we connect it there. That's how virtual interfaces need to be connected. So this was the first port, and it gets connected to the port declared inside the sequencer. And then we look at the other ports. Actually, on the stimulus generation side, most of the ports are in the base classes, and on the monitor side, all the ports are visible. So, but let's look for each one of them from the beginning. Searching for port. Port. So this was the first port, and it gets connected to the export, which is inside the other sequencer. Okay. Then at next item, try VPI port, analysis port. So let's look at this analysis port. So there is a analysis port which takes a sequence item of this type and which gets connected, which has a name, SHA3 port. And there is an analysis implementation which has a name. So we have a SHA3 monitor, and okay, I think this is becoming a bit confusing. So what I'll do is I'll pull up the diagram. So I'll pull up the diagram here. So we are talking about SHA3 monitor. This is the SHA3 monitor, and SHA3 monitor is connected to the collector, or the name of the collector is AVL monitor. So SHA3 monitor should have an export which gets connected to the port of on AVL monitor. So that's the export or implementation. Actually, in this case, it's implementation. And we have AVL analysis. So this should get connected. AVL analysis should get connected to the collector. So let's see where it's getting connected here. So response port from the, just 1 minute, from the monitor, there is a response port. So this is the AVL monitor. Okay. So AVL monitor has an instance name which just says monitor, and the response port is getting connected to this collector. This export over here, this implementation port on the monitor. So now connect and the response port. Why is it this way? I don't see response port as a monitor, and there is an agent. Inside the agent, there is a monitor, and monitor, this is the monitor we are having, AVL monitor. And AVL monitor, it's actually, this one is a VPI component, and therefore the same thing, this VPI monitor component has a port in the base class, and as a result we don't see it. So that port is called response port, and it's getting connected to the analysis port. So that's how these two components are getting connected. And from the monitor to the scoreboard. Okay, so from the monitor to the scoreboard, we have this one, SHA3 monitor. Yeah, SHA3 port gets connected to the scoreboard analysis. All right, SHA3 port gets connected to scoreboard analysis, SHA3 analysis. And SHA3 analysis is this, SHA3 analysis. And uh, as you can see, write function is the one which will be called when something is put into this port. And what we have done is, in this case, we look at whether it's a write or read request. So all the transactions from the collector, this collector as well as this collector, actually this connection has to be here. So after another monitor. So all the transactions come on the same write function. So let's change that. Okay, we'll get some idea also. So what we'll do is, instead of one write function, we'll create two write functions. So one of them for the stimulus for the input side and one for the output side. So we name it write request. One of them is request, the other is response. Actually, it won't work this way, sorry. Actually, as I told you earlier, there is no collector like this. It's the same bus. There's only one Avalon bus, and there's only one collector. And this collector is going to the monitor and to the checker, because all the read and write transactions are coming on the same bus. Okay, so there are no the output of DUT is not segregated because it's a memory map bus, so it's not segregated from the output. And the only difference between the transactions is that it's either a read transaction or a write transaction. So if it's a read, that means I'm creating an address and giving it a read, and then the read sequence is generated that way. If it's a write, the write sequence is generated, and both of them go to the same write function of the checker. Had we got two different interfaces and two different collectors and so on, then we could have created two write functions with different names over here, and that way we could have a different kind of checker there. All right. So having said that, okay, just some more things. So So let's look for other port connections. So this one is the hidden port. I mean, this gets connected to the hidden port, which is inside the sequencer implementation. So this gets connected to the sequence item port, which is a standard port inside. You can, if you want to have a reference, then this is where it goes. So if you look for inside UVM, and there is something like UVM sequencer, UVM sequencer, and inside UVM sequencer, actually we'll have to um, look for sequence item port here. Grep sequence item port. This is where in the parameterized base class. So you see some references to sequence item port, not complete. Sequence. Okay, something is wrong. So it's not defined here. That means it has to be inside TLM, and there is a sequencer connection over here. This one. Okay, so it must be inside this. Not even here. Let's check where is the sequence item port. It's this that sequence item port. Okay. Sequence item port. Okay, so we have in the driver. So transaction sequence item port. Where is it defined? So it's inside the driver actually. So the driver has a sequence item port. Okay. So I need to look at the code again, and so this is actually going to the I needed to look for, sorry, I needed to look for export, and that's why it wasn't visible. The sequencer has an export, not a port. So my mistake. So inside UVM, I look for export, and that will be there inside the sequencer. So here it is, sequence item export. Yeah. So we have a sequence item export, this one. So this is named slightly differently with underscore over here because of the multi-core stuff we need to do. So what happens is this is where we define it, and because we have a immutable sync tag over it, it will automatically create a proxy function which will have sequence item port as a name. So just so that we are able to have multi-core uh, simulations with this UVM. So it's named slightly differently. It has a sequence underscore sequence item port as name. Okay. So, but this is where it is getting connected to, and then monitor is getting connected to the upper layer monitor, and this monitor is also getting connected to the upper layer monitor is getting connected to the scoreboard. So these are the connections here. So let's look for more stuff. Connect phase. Yeah. So this is where we check. This is agent. This must be agent. So inside the agent, we check for whether the agent is active or not, because that's like whether the driver and all these are active or not. So we check for that, and then only we connect with the sequencer sequence item export. We connect the driver to. So in case of driver, we connect to sequence item export. In case of virtual sequencer, because there is another sequencer sitting on top of it, we'll again be connecting to sequence item export. Okay, that's how it works. And I would have liked to do some experiments here, but I don't think we have time for all the experiments. I'll just conclude this session by also saying like how the driver and monitor get connected. So if you want to in embedded UVM, so if you want to look at that from the beginning, so you just need to search for VPI. So this is your data flow, um, like how data a transaction will be conveyed to the BFM. This is where it this is how it gets done, and the components which are doing it, they always have VPI func as first of all their name will be will have they'll derive from VPI driver or VPI monitor, and they'll always have they want to pass the name of the function as a parameter, so that for example, let me show here. So I have a driver, and this driver, when it gets instantiated, okay, it still gets VPI string as a parameter from top. So we need to see what gets passed to the VPI string parameter, and AVL gets passed to VPI string parameter. So this is the string. Okay. Um, Again, this is agent level. So agent level would mean agent will have like inside this agent, we see the agent is having a driver as well as a monitor, and the same VPI string is getting passed to the driver as well as to the monitor, right? Here, driver and monitor. Okay, so what will happen is it will create two components, and both the components have AVL string prefix. Okay, and now inside the BFM, yeah. Now inside the BFM, wherever there is $AVL, yeah, yeah. So it will be suffixed with try next item for getting the next item. So this function will be created by the driver. And since we passed the same string to the monitor as well, this put function is coming from the monitor. This is coming from the driver. This is coming from the driver. This put function is coming from the monitor, and it's putting the transaction back to the monitor. So there's one driver, one set of functions from the driver and one function from the monitor. So that's how the BFM gets connected to the respective driver and the monitor. So the same thing we can check with AVST header, and here in the test bench, we have two separate BFMs. So actually three BFMs. One BFM is for the driver. This one is from the driver. And AVST is coming as the prefix here, and AVST over here. Now this BFM doesn't connect to the monitor. There is a BFM here which has AVST request as input, as the prefix string. And there is another one, AVST response. Okay, so this goes along with the union test bench here. And if you search for AVST as a string, you know, yeah, here. So the monitors are getting connected with AVST request and response, and the driver is getting connected with just AVST as a string. So all this combined makes the whole the internal ports and ports of the driver and of the request monitors. These internal ports, which are defined inside the VPI components, they again they need to be connected. So this is how we are connecting. The egress port is getting connected to request analysis, and the egress port is getting connected to response analysis. Similarly, for the driver, a sequence item port is getting connected to. Okay. All right. So this is how this all takes place. I hope. I mean, ultimately, you have all these test benches with you in case something is not clear. You could ask the question. But right now, it's time for a small 15-minute break so that we can have the test in 15 minutes and you can get some rest. So that's the end of it. So I'll give you a new release tomorrow or day after morning, and day after we'll go through QEMU. That's actually pretty interesting because we'll interface the simulation with an emulation, a software emulation stack, and we'll transfer